Okay. Yes. You can see the PDFs, right? Yeah, fine. I'm audible right now. So, hello guys, myself Fazil, and I'm here to teach you the engineering physics with the topic of laser. So, okay, now I'm going to start the topic about the laser, and later we'll continue with the other topics like quantum mechanics and stuff. So, we thought laser would be a perfect kickstart to revise. So, let's dive in. Okay, so what's essentially a laser? Laser, it, the full form of it is light amplification using stimulator emission of radiation. So this pretty much gives the idea of what laser is. So first, uh, let's see about the characteristics of the laser. Okay, it has high coherence, directionality, polarity and stuff like that. Then in this course, we are also going to see about the absorption and emission of the radiation, Einstein coefficient related to this laser, population inversion, and that's a mechanism that is going to make the laser work, pumping and achieving population inversion, how we are going to do that. Then what's the three types, three level and four level laser systems are there, and we are going to see what the types of lasers, that is CO2 laser, Nd:YAG laser, and semiconductor lasers, and what are the applications of that. So let's see what a laser is. A laser is a device that emits a narrow intense beam and of light through the process of stimulated emission. So we have pretty much seen laser, we have played with it, we have bought it, and yeah. So this laser emits this light using a process named stimulated emission radiation. Okay, so these lasers are typically made of gain medium, a system of mirrors and a power source, which we will be discussing later. So when an electric current which is given to that laser, uh, the electrons in that gain medium gets excited and it gets to the ground state, and with that action we will receive the photons, and that's what becomes that light light which comes out of stimulated emission radiation. So the basic principle of this is given in this fourth point, as you can see. Am I audible, guys? I'm just checking at this point. Just give a thumbs up right now. Yeah, fine, I can see. Okay, in the fourth point, you can see these photons. This fourth point basically explains how the laser works. The photons, which was came out as an effect of stimulated emission, it bounces back and forth in the mirrors that is present in that laser mechanism. Okay, which gives ways to produce even furthermore some of the photons. Okay, so which will again go into that cycle, and it will go back and forth, and it will stimulate other photons, and it will happen until the supply of the energy supply is given to that laser. So that's how laser works on a superficial level. Okay, so lasers have wide range of applications, including industries in like you can use laser for cutting and I mean holography, and for sensor technologies and stuff like that. For basically, and for more importantly, it is used in communications, as we are going to learn it in optical fiber communication later. So let's see about the properties of laser. It is directional. So if you have seen the laser, you have noticed that it doesn't diverge a lot. It goes in a straight line from the source to the end or wall or something like that. So laser light is highly directional. It is focused in a single narrow beam that travels in a straight line. So this is why these lasers can be used for processes like welding, drilling, cutting, and stuff like that. So monochromatic. Have you ever noticed that lasers are only in single color, either red, blue, green, like that? It doesn't have another any other wavelength, light with another wavelength. So it only contains a single wavelength. So that is monochromaticity of this laser. Then coherence. uh you might have studied in 12th what the coherent waves is, that every wavefronts that is in phase is called coherence. So this coherence of the lasers used to produce a narrow beam of light which can travel a long distance from the source of the laser. Intensity. So laser light are highly intense. because it can carry lot of energy as it is narrow and it can be pointed to a single point. So they are very intense. So as you can, so it is directional and intensive. It is very intensive. It can be used for processes like cutting and stuff. Polarization. Uh, so laser light is highly polarized because of the electric field of that light waves oriented in a specific direction. So this polarization helps in some of the researchers and from high end stuffs like optical communication and spectroscopy and holography and stuff like that. Okay. So basically, laser is just an abbreviation of light amplification by stimulated emission of radiation. So let's, as you can see here, the directionality. In an ordinary light, you can see the divergence is higher, but in laser it doesn't. The directionality is so straight. Okay. Then in monochromaticity, the delta V, the frequency, the change in the frequency pulse of that laser is almost zero. So the light coming out of the laser contains only one wavelength of light, and so that's why it is monochromatic, highly directional. It is due to the characteristics of the stimulated and because of the cavity from which the lasering action is produced. Okay, so in here the angle of divergence is given as A2 minus A1 divided by 2D2 minus D1. So this basically gives how much that laser light has diverged. Okay, so that is here you can see the divergence is equal to dr divided by dx. That is rate of change of the radius with respect to the length of that laser light which has traveled. Okay, so that is A2 minus A1. That is the difference in the radius, and the D2 minus D1 is the distance difference in the distance traveled by the laser. So this basically gives the angle of divergence of that laser. But in laser, you can see this value is very low. So it means that the divergence is very less and the direction. So that laser is highly directional. So yeah, this slide basically tells about that. Laser light has very small divergence. It is highly directional. The beams come from the cavity resonator and only waves. Okay, so if you have studied, you might have known that the cavity resonator have two mirrors. I will further explain it, but uh, to explain this slide, I will just say it. As you can see, there are two mirrors with one has a reflection of 100 percentage and another one with 99 percentage or slightly lower. So when that reflection happens, the beam of light, that is the photons, which is perpendicular to that 99 percentage reflective mirror comes out straight. Okay, so that, so then only it can escape that cavity. So that's why it is highly directional. So the directionality of the described light can be given in divergence angle. Okay, it is given as theta d, which is equal to beta lambda divided by capital D. Here, lambda and capital D are wavelengths and diameter of that beam respectively, and beta is sum of the coefficient which can be related to that theta. So as as it is given here in a laser light, the wavelength and with the diameter and with the beta coefficient, if we substitute that, we are getting a degree a divergence angle of 0.003, which is very smaller compared to other lights such as a searchlight or flashlight. So as you can see, the searchlight has an angle divergence of 8 to 10 degrees and normal flashlight 20 to 30 degrees. So you can see how how very less that laser is getting diverged. So monochromaticity. So laser waves, I mean the laser light is highly monochromatic, and which depends on the property of the medium in which we are going to use the laser, and the reflection spectrum, and the cavity resonator, and the feedback mechanism basically. So as you can see in the paragraph 2 in this slide, a laser cavity forms a resonance system. The photons are emitted by the stimulated emission, wherein all the photons are in same phase and the same state of polarization. So basically, when that photons come out of the cavity, it is all are in a same phase, that is coherent and in a state of polarization. So this oscillation can only sustain when the frequency is in resonance of the cavity. So this leads to a narrow of the laser line width. That is that diagram given above. As you can see, the delta V, the change in frequency, is very less when lasing action takes place. So the light is usually very pure in wavelength when it is come out during the lasing action. So this is the third property, that is coherence when there is no change in wave that all waves friends are in the same phase. And intensity is slightly intense. Uh, on what is what gives like 10 to the power 9. Okay, as I've already explained what a coherent source is, so let's go here. In physics, coherent sources refers to source of waves. In taking the laser, it is a coherent source. First, as I have said, coherent sources contain the wavefronts which is coming from the source, and it is in the same phase. Okay, so these two sources of waves are considered coherent if the phase difference remains constant over time. This uh, this can be achieved using single source of wave, like a light source, or are they using two separate sources but with synchronized with some external means such as oscillators. So as you can see here, the coherent sources do not cancel out each other, so they can travel out for a maximum distance. But when it is an incoherent source, the waves, the phase difference does not match, and it can cancel out within a given time. So coherent sources are very important in physics so that they can perform some of the experiments in physics, like in optics, acoustics, and quantum mechanics. So coherent sources are used in holography, interferometry, and communication technologies. So coherent source is essential for to perform all these. So basically, this slide tells uh, a what is a coherent source and how laser is coherent. Okay, there are two types of coherence. That is temporal coherence, and then there is spatial coherence. Okay, now let's take a fixed point of a wavefront. Okay, if uh, the time let's note that wavefront at the time t, and at again time t plus delta t. Okay, so if in that position that wavefront has the same phase with the given two different times, that is t and t plus delta t, so then we can say it is temporally coherent. So so with the same thing, it is analogical to spatial coherence. So we can take 2 points, that is x and y of the wavefront. Okay, x and y. Let's take at time equal to 0. We have to note that phase differences between this point x and y. And if for any time t greater than 0, if the phase difference remains same between those 2 points, then we can say it is spatially coherent. So this is the two type of coherence that is given here. So basically, how to achieve this spatial coherence is that we have studied about this double slit experiment. When a single source is given and slit 1 and slit 2 is present, then these slits acts as a source, and these slits produce the wavefronts which will be coherent. Okay, this is all about the part 1 of laser physics. Then we'll move to part 2. So let's move to the part 2 of laser physics. Uh, this is just a simple question about the brightness of the laser source. Okay, so let's take the given ordinary light source and laser light source. Let's assume that both has the same number of photons. Then what is brighter, or is both the sources equally bright? So as we can say, no, they both are not equal. We'll perceive that the laser is somewhat brighter than the other source. That is because of the properties that we have discussed in the previous PDF. So, like it is very coherent and directional, so that's and highly intense, and it is monochromatic, right? So that's why we perceive that it is brighter, even though both the sources have same number of photons. That's what given in this slide. Okay, it just goes through the earlier history of how this laser is invented. That's with this Albert Einstein's paper, which he published, and then yeah. So these are spectral output of types of layers. Sorry, lasers. So you can see copper vapor laser, argon laser, India laser, ruby laser, uh, CO2 lasers and stuff like that. So it again gives what are the main characteristics of the laser, that is highly intense, highly monochromatic, highly coherent, and high. Uh, yeah, two times. No. Okay, okay, fine. It basically gives a recap of the part 1 PDF. That is the angle of divergence, and what a spatial coherence is, what is a temporal coherence is, and yeah. Okay. Now let's see about the Einstein's coefficient. So we all know in between energy levels in an atom, which energy can be given in form of h mu, that is Planck's constant multiplied with the frequency. So, which is essentially the excitation energy required for that electron from the ground state to travel to the excited state. That is, in this diagram, it is traveling from E1 to E2, right? So, so that is basically the energy level of E2 minus energy of E1. So, so we have created some of the assumptions, that is RAB, which is Einstein's equation rate of absorption. So B12, okay, B energy level 1 to 2, that is absorption coefficient, that is it absorb the Einstein's absorption coefficient when that electron is jumping from E1 to E2. Okay, so the formula given here is that Einstein equation rate of absorption is equal to B12, that is Einstein's absorption coefficient of absorption, that is going from E1 to E2, multiplied with N1, the number of atoms in the ground state, that is number of that's not atoms actually, that is electrons in the ground state E1, and U mu, that is the density of the radiation. I mean, how many then I mean the radiation energy that is given to that E1 electrons, that is the ground state. Let's talk about the emission. So there are two types of emission. First one is spontaneous, and the second one is stimulated. So what is spontaneous is when there is no external without any external energy, when the electron in the E2, that is the excited state level, comes back to its original ground state level. So when it comes, we know that it ejects photons, right? That photon will be given with a frequency which is equal to E2 minus E1 divided by H. As we know, the energy difference between E2 and E1 is the energy of the photon. So the frequency is essentially E2 minus E1 divided by H. Okay. So basically, it directly comes from E2 to E1. Okay. So, but basically, when this happens, when it goes from ground state to excitation state and comes back to its ground state, the lifetime of that is just 10 to the power. Hello. Oh, oh, I was in not sorry. Wait. Uh, Rookie mistake. I was in mute. Okay, shall I go from the start? Can I continue from here? Just reply me. Sorry guys for that.
Yes, no.
Can you message me? I can hear right now. I mean, because of the software running in the background, so I can't hear. Can you message me? Shall I continue from here, or shall I start from the beginning? Yeah, sure. Fine. Okay, so let's start this slide. Uh, is the brightness of the laser source equal to an ordinary light source with the same number of photons? It's just a basic question. So if we see that, yeah, we can test it out with in our home. No, we can see that the laser source is actually brighter than a normal ordinary source, even though it has same photons. Let's assume that it has same number of photons. Okay? So brightness is essentially the perceived intensity of light. Okay, so what we perceive is what called as brightness. Okay, so as you as in theory, lasers are actually highly intense. Okay, that we have saw in the previous PDF, right? So even though both sources have same number of photons, we perceive that laser light is actually brighter. Okay, so this is what a simple question given by sir. Okay, so this basically gives a small history about how the laser is invented. Okay, first it all started with Albert Einstein's paper. So this slide explains just about the spectral output. Okay, the spectrum in which the laser can operate. That copper vapor laser, indiac laser, argon laser, UV lasers, and CO2 lasers and stuff like that. Okay, so this is just a summary of what we have learned in the previous PDF. Okay, that the laser is highly intense, highly monochromatic, highly coherent and stuff. Yeah. It, yeah, it gives about the angle of divergence, spatial coherence, temporal coherence, and like that. Okay, now let's see about the Einstein's coefficient. So let's talk about the process of absorption here. Okay, so when an external energy comes and attacks, okay, let's say it attacks, okay, attacks electron in the ground state. Okay, so it gets excited with that energy and moves to the excited state E2. Okay, so the energy required for that electron to move to E2 is essentially E2 minus E1, the excitation state minus the ground state in which that electron is. Okay, so which is h mu, that energy we have to give is equal to E2 minus E1. Okay, so RB, rate of absorption, okay, or AB, which is Einstein's equation of rate of absorption. Okay, which is given here, and B12 is just a absorption coefficient, that is B12 from 1 to 2, that is from E1 to E2, that is the absorption of the energy happens here. So here the equation says or AB is equal to that absorption coefficient into N1. That N1 is number of electrons, not atoms. It is given atoms here, not atoms, electrons in the ground state. E1 into density of radiation. So that U mu is density of the radiation that attacks at E1 E1 energy level. Okay. So now let's see about emission. There are two types of emission. One is spontaneous emission and another one is stimulated emission. So let's first see about the spontaneous emission. So this happens when no external energy is given to that atom. Okay. Here the lifetime of it is 10 to the power minus 8 seconds. Okay. It is basically used in LEDs to emit the light. Here, as you can see, the electron from E2 to E1 gives a frequency mu, which is equal to E2 minus E1 divided by H. That is the energy formula basically. Okay. So, uh, but here, uh, but here you can see the lifetime of that uh, emission is just 10 to the power minus 10 seconds, which is very low to perform the lasing action. So, with spontaneous emission, we cannot perform the lasing action. Okay, then uh, then let's see in spontaneous emission, that is RSP, rate of spontaneous emission, which is which is given uh, which is given with 8 to 1, that is Einstein's coefficient, that is 8 to 1. Observe A, that is 2 1, that when that electron comes from energy level 2 to energy level 1, that is excited state, to its ground state. And N2 is here gives the number of electrons in E. Okay, so in stimulated emission, it happens with the help of an external energy. Okay, so in stimulated emission, there is a meta state. Okay, in where in that meta state, that electron stays somewhat in between 10 to the power 6 to 10 to the power, sorry, 10 to the power minus 6 to 10 to the power minus 3 seconds. So with that we can perform that placing action. So in stimulated emission, which is basically used in laser. So RST, which is R of stimulated radiation, is equal to B21. That is Einstein's coefficient of that emission from level 2 to level 1, and N2 is number of electrons in it, basically. So the relation between this Einstein coefficient. Okay. So here you can see the Boltzmann distribution law says that the population in ground state multiplied with e to the power minus e divided by kT, that is t, where T is the absolute temperature and the E is the energy level of energy of that energy level. It gives the number of electrons, right? So with this, for E1 we are calculating the number of electrons, that is N1 is equal to N naught E to the power minus E1 divided by kT. For energy level 2, N2 is equal to N naught E power minus E2 divided by kT. We are substituting that energy levels and getting N1 and N2. When we divide it, we get N2 divided by N1 is equal to E to the power minus E2 minus E1 divided by kT. So we basically know that E2 minus E1 is H mu, right? So we can substitute H mu instead of E2 minus E1 in that previous equation that we have got. So it becomes N2 divided by N1, which is equal to E to the power minus H mu by kT, which we can uh, take the reciprocal to get N1 divided by N2. So so here rate of emission is equal to rate of absorption. So what the electrons has absorbed will be again given as an emission, right? So here the stimulated emission and the spontaneous emission, which is equal to that absorption rate. Okay, the rate of stimulated emission and the rate of spontaneous emission is equal to the rate of absorption. Okay, with the Einstein's equation that we have derived above, B21 into u mu, that is the rate of stimulated, and sorry, rate of yes, it is stimulated, yeah, rate of stimulated stimulated emission, and plus A2 minus A21 N2 is equal to B12 N1 u, u mu. So this B12 N1 u mu is basically that rate of absorption. So with that we can get the energy density formula by substituting. Okay, so A21 N2 divided by this will give this u mu by taking by bringing B2 the B21 N2 u mu to the right hand side of that equal sign, and then taking a u mu common and dividing the other term. So we'll arrive at this point. Okay, so u mu, that the energy density is equal to A21 N2 divided by B21 N2 whole multiplied by B12 N1 divided by B21 N2 minus 1. So energy density formula can be derived from quantum physics and semiconductors, I guess. So So which is 8 by h mu 3 divided by c3, 1 multiplied by 1 divided by h mu by kT minus 1. Okay. So with this, uh, with Planck's radiation law. Okay. So here P21 and P12 can be considered as a single B. Okay. So if we substitute that, we can arrive at, if we take an analogy of this, we can arrive that A21 divided by B21, that the ratio between absorption and the emission coefficient is basically 8 by h mu 3, mu to the power 3 divided by c to the power 3. Okay. So here let's see about population inversion. Okay. So this is a very important principle from which the lasing action can be achieved. Okay. So population inversion is very much required for stimulated emission. Okay. So with which we can achieve that lasing action. Where, as you can interpret from that name, population inversion is when the given electrons in the are in more number in excited state than in the ground state. Okay. So as you can see here, population inversion in this, E2 has higher number of electrons than E1. Okay. So here stimulated emission in this state can be negliged as spontaneous emission. Mm, yeah, in so the stimulated emission in elevated state is negligible because the energy gap is very much higher. So the lifetime will be short, so that the stimulated emission cannot be done in the elevated state in an elevated state. Okay. So we can see in N1 is the number of electrons in low level and high level E. So where N1 is less than N2, it is basically given that the population function has been achieved. So in normal equilibrium, when the energy doesn't give, when we don't give energy, the N1 will be obviously higher than the N2. So stimulated emission can be only achieved when population inversion happens. Okay. So this basically gives the metastable state. Okay. Explains about the metastable state. So metastable state is basically there is a state which exists between E2 and E1, where that excited electrons can be somewhat further be placed so that it can have an extended lifetime. Okay. So the medium at which the population inversion can occur is called an active medium. So we have ADAG, CO2, and semiconductor laser. Okay. So when this population inversion happens, where it happens is called active medium. So CO2 is an active medium, semiconductor is an active medium, stuff like that. Okay, let's see about the metastable state. So has a longer lifetime. Yeah, as I said, to achieve lasing action, it must have longer lifetime. So which provides to 10 to the power minus 6 to 10 to the power minus 3 seconds. So mid-level created. So stimulated emission is increased when a metastable state is introduced between E2 and E1. Okay. So E when the electrons from ground state go to E2. So here you can see from E0 to E2, and it comes back to that E1, that is metastable state. From in the metastable state, the electrons should have higher number than in E0. So you can essentially say that population inversion has occurred. Okay. So pumping is basically taking that ground state electrons to the higher excited state. So we can achieve that pumping using optical pumping, like using light for pumping the electrons, and atom-atom collision. That is when we use the CO2 laser, where we use an atom to collide another atom, from which we can get the energy. And electric excitation is just we use an electric discharge, and chemical pumping is when you use a chemical reaction to pump those electrons to the excitation state and to achieve metastable state. And yeah, so let's move on to the third part of laser physics. Okay, so this part essentially explains how does laser work, what is the lasing action, and how to achieve it. For a given resonator, how much pumping we need to initiate that action. So for the lasing action to happen, how much we have to give the energy to that laser. So some of the laser can only be operated in pulse mode. So if you can see, I guess in India, the three level lasers can be only used in upper state. Okay, so in some of the clinics for hair transplant, you can see the laser can be is pulsed. Okay, so some of the lasers can only be used in pulse. That is when it is using a three level mechanism. Okay, so let's talk about it later. Yeah, so this PPT explained how the lasing action start, how to achieve the threshold population inversion so that the lasing action can be further achieved, and the three level and four level pumping schemes, and what these Nd:YAG and CO2 lasers are. Yeah, so this is what a laser system totally is. It has an active medium, a pumping mechanism, a fully reflective mirror, a partially reflective mirror. So the partially reflective mirror is not half partial and half reflective. It's more reflective, but very much lesser refractive. Okay, I mean which is transferred. Okay. So with which using this mirror, the laser, the photons from that active medium can escape out. Okay. So basically, active medium which contains the atoms to be excited can be solid or liquid or gas. Like semiconductors are solid and CO2 is gas, so we can use pretty much three states to achieve this lasing action. So let's see pumping mechanism. This mechanism is used to excite those electrons in that atom. Right? So optical cavity is that two mirrors placed in that I mean, so between these mirrors, this active medium is placed. So this is called the optical cavity. So okay, let's dive into how that laser works. Oh, let's see how the lasing action works. Okay, once the pump is switched on, that is when that electron in the active medium is excited to the opposite. So initially, a spontaneous electric photon triggers immediately. Those stimulated photons travel axially through the excited medium. Okay, again travels through that active medium, it triggers another photon to be produced from that active medium. Okay, so it creates a chain reaction like in nuclear fission. So when this again triggers furthermore stimulated photons, okay, that way undergoing amplification. That is the number of photons getting increased. Okay, so the mirrors are there both of the end just reflect those photons. Okay, reflect back the photons at the end of these devices. Okay, it goes from the N1 to the N2 back to N1 and it just reflects. So with that reflection, that photons generate another stimulated photon from that active medium. Thus, it amplifies the laser. Okay, so these actually traveling photons undergo further amplification for each pass through the resonator formed by the active layer. So as I said, with each pass it generates more and more stimulated photons, right? Yeah. So stable laser emission is initiated. That is when that stable laser action starts when the gain per pass through the resonator becomes loss per pass. So in each of the cycle, when the gain is equal to the loss, so as in the reflection, the energy gets lost. So when that loss is equal to the gain, it reaches the stable state of the lasing reaction. Okay, so the minimum population inversion that's needed to maintain the gain per loss and loss gain per pass and loss per pass through the resonator is called the threshold population inversion. So we must make that threshold so that the lasing action will be stable. Okay, so as you can see in this image, so as you can see in this diagram, when the pump is turned on, you can see some of those simulated photons travel. Okay, so when a laser is pumped, the photons are spontaneously emitted first, and then it returns to the lower excitation state. So first it creates a spontaneous emission. Then these spontaneous emissions trigger the stimulated emission, and then this cycle goes on and on. So as you can see in this second end, a photon gets out, right? So that is when it is perpendicular to that mirror. So when that's when it can escape. So and as the pump is on, you can see the chain reaction begins, and the photons inside that cavity becomes exponentially larger and larger with the advancement. And so with that, that lasing action starts, and when it reaches the threshold population in question, you can see that it all are in the same coherence, and which gives the coherent laser out of that cavity. So when those photons that are not perpendicular to that mirror, it gradually loses its energy by going, I mean, traveling inside that, passing inside that medium. So it loses the energy, and only the actually moving photons sustain the energy. So the lasing action at that time gets to that equilibrium point, that is the threshold population conversion gets achieved. So the lasing action is now completed. So this is basically how a laser works. Okay. So as I have said earlier, the gain per pass must be equal to the loss per pass. So that's when the threshold is achieved. That's when the lasing action will be stable, right? So let's take a cavity with a lens and mirror with a reflector reflectiveness of R1 and R2 given in this. Okay, so absorption per unit length of this cavity is given as A, that is that loss, and the gain coefficient G is given, that is gain per pass. Okay, that is loss per pass. This is gain per pass. Okay, so this gain arises when the stimulated emission is present and therefore proportional to the population inversion. When the population inversion is higher, this stimulation, this gain of the stimulated emission is higher. Okay, so let the stimulated emission be average intensity I naught. Okay, start from M1, that is in this region it starts. Let's assume. Okay, and it travels axially, that is perpendicularly to M. Okay, so when the stimulated emission intensity, so the intensity at M2, when that photon reaches at M2, what's the intensity is given as I naught e to the power g minus a. So gain minus loss multiplied with L. So the unit length that it has traveled, right? So yeah, and when it reflects back at M2, right? So it is it has a reflectivity of R, and that M2 has a reflectivity of R2. So we multiply that R2 with that stimulated emission intensity after it reaches M2 and goes back to M1, right? So which is R2 I naught e to the power 2 gain minus a, gain minus loss into L. Okay. So again it reaches to reflected from the M1 mirror, right? So again it is reflected with the reflectivity of that mirror R1. So we have to multiply that factor, right? So R1 R2 I naught e to the power 2 g minus a multiplied by L. Okay. For the sustained oscillation, that is after R, when it goes from mirror 1 to 2 to back to 1, it is 1 pass. So it must sustain the same intensity. So that formula that we have derived must be equal to I naught. So basically e to the power 2 g, that is gain minimum minus a into L is equal to 1 divided by R1 by R2. When we take the log in both sides, we get 2 g min minus a into L, which is equal to ln 1 divided by R1 R2. So substituting this, we get, I mean, yeah, we get the gain minimum is equal to a plus 1 by 2 ln of 1 divided by R naught. Okay, so this gain must be achieved to get the sustained lasing action. Okay, so this is basically the derivation of the gain minimum for the mass. Okay, so there are two types of pumping scheme. Okay, first is three level laser system, then four level laser system. First three level laser system, in which the electron goes from E0 to E2 and comes back to E1. Okay, so in E1 the number of electrons will be higher and it will achieve a population inversion, and when it comes from E1 to E0, the photons will be that stimulated photons will be released. Okay, so here pumping, metastable state, and laser action. So this is the basic thing in three level laser system. In four level laser system, it goes from E0 to E3. Okay, from that it goes to E2, and from that it comes to E1 and E0. So it has four steps in that cycle. Okay, so in E2 and E1, between E2 and E1, it achieves that metastable state, and the lasing action happens between the E2 and E1. Okay, and so here you can see the stages are pumping, then it achieves achieves the metastable state, and then it has a new state that is short-lived energy state. Okay, where the laser action happens. Then it comes back to the ground state. So here, upper laser level, the metastate will higher energy level where population inversion is created. Upper laser level, that's where the population inversion is created. Then in lower laser level, energy back, it is where the electrons comes back to. So it is the lower laser level. So to create N2 greater than N1, we need to pump more than N naught divided by 2, right? So we have to give more number of electrons from a N naught, I mean N naught by 2. So that to achieve that, it is somewhat difficult. So that's why that in three level mechanism we get the lasering action where in a pulse manner. Okay, but in four level system, the pumping level from ground state it goes to the excited state, then it comes to the upper state, then lower state, right? So here it is easier to achieve that and maintain the inversion. Okay, because that one it has the original ground state and the only one metastable state, but here it has two. So it can the electrons can be maintained between those two metastable states, right? So as you can see, the ground laser level is not equal to ground level, the original ground level. So this is basically the three level pumping system and four level pumping system. In three level pumping system, we can get only pulses of laser, but in four level system, we can get a smooth lasing action. Okay, so this is basically the classification of lasers. Okay, based on the active medium. First, it has gas lasers, then solid state lasers, then liquid and semiconductor lasers like that. Okay. So based on wavelength, we have visible, that is RGB and some laser like that, IR and UV laser. Based on pumping mechanism, that is how we pump the electrons from ground state to the high state. It has optical, chemical, and electric discharge. So based on pumping scheme that we have seen right now, that is basic, three level pumping scheme and four level pumping scheme. Based on output, it has class 1, 2, 3, 4. We don't have that. And 2V laser is not also included in this. Okay. Let's go to the part 4 and part 5 of laser. Okay. This basically tells about the types of laser and how it works. Okay. And part 6 pretty much contains the same semiconductor, how working of the semiconductor laser. Okay. So I guess it is pretty, I think it is out of syllabus, right? Yeah. The sixth part. Yeah. Here is the types of laser is the fourth portion. Semiconductor lasers. Okay, now let's see about the types of laser: NDR, CO2, and semiconductor laser. Okay, so let's first see about the laser system. Okay, so that we have previously seen. So first, we must choose the material that will give the given uh, wavelength of the interest. So we might need a wavelength for red, a different wavelength for green, different wavelength for blue, right? So we have to choose the required material which will give the photons of that desired wavelength. Okay. So and we have to choose in which pumping scheme we have to do for maintaining the population inversion. Okay. So then optical resonator cavity to make to achieve that pass of that stimulated emission across the cavity. Okay. So pumping mechanism, active medium resonator is what we need all for a laser to perform. With one mirror with 100% of reflectivity and another one slightly lesser than that. Not 50-50, but slightly lesser than that. Okay. So first, let's see about the NDR laser. Okay. So Nd is neodymium, I guess. Then Yag is yttrium, aluminium, and garnet. So which has the formula of Y3Al5 water. So this laser gets the pumping mechanism of optical krypton flash lamp. Okay, so it gave the excitation happens with the help of optical pumping mechanism, and the pumping scheme is given as you can see in the diagram. It is a 4 level pumping scheme. Okay, so it pretty much I think the point 5 is pretty much the same as of all the laser. So first, spontaneous emission triggers the stimulated emission, then which is feedback by the mirrors for the repeated amplification, and then at the threshold, it maintains the lasing action where the gain per pass is equal to loss per pass, so the laser gets switched on. So I don't think you need to keep in mind about these wavelengths of those. Okay, so just skim in the application of the lasers. Okay, so Nd:YAG is used for welding, drilling, and for eye surgery and stuff like that. Okay, then let's see about CO2 laser. So here CO2 laser uses obviously CO2 gas, N2 for resonator transfer, and helium for low to depopulate lower laser level in ratio. In this CO2, N2, and He are in the ratio of 1 is to 4 is to 5 in that laser cavity. Okay? So pumping mechanism is electric discharge, and pumping scheme uh, resonant transfer to metastable state, which is a vibration level. I guess it is a 4 level scheme. Yeah, it is a 4 levels. So first, we need to understand the movement in CO2. As you can see, the C, that is the carbon atom, is in the center, and O is in the either side of it. Okay, so here it is called as 0, 0, 0 stick. Okay, and when it is in the symmetric mode of vibration, the O atoms simultaneously goes away from the C atom and comes to it. Okay, so it is symmetric mode of vibration, and in bending mode, the two O atoms goes up and C comes down, and vice versa. So this bending mode of vibration. In asymmetric mode of vibration, you can see that when one O atom is coming towards this C, one O goes further. Okay, so this is a then vice versa happens. So this is asymmetric mode of vibration. Okay, so energy set into molecule in vibrate bending mode is lesser, and the symmetric mode is higher than bending mode, and anti-symmetric is higher than the all other. Okay, so which is represented by the numbers. The symmetric mode is represented by the number 100, bending mode with 0, 0, and asymmetric mode with 0, 0. Okay, so the construction, let's see. Okay. First, the electric discharge, that is the pumping mechanism, excites the N2 atom. When this excited N2 atom collides with the CO2 atom, and this this transfer, when this collision happens, this causes the molecules to vibrate in it. Uh, so when this collision happens, the upper state level is created. First, the spontaneous emission is triggered, and the CO2 relaxes to the symmetric and bending mode of vibration. Okay. The population inversion is maintained and by the continuous electric charge. So N2 is required to maintain the population inversion. Okay, and yeah, it is given that small diameter of tube and high thermal capacity of helium aids in depopulating lower laser level. So when the lower laser, when electrons comes to the lower laser level, it must go to its ground original state, right? So helium helps with that. So N2 helps with maintaining that metastable state of the CO2 atoms, and helium helps with depopulating that lower laser level. So this is how a four-level system is achieved. CO2. Okay. So efficiency of it is 30% and voltage requirement is 8 kilovolt per meter. Okay, okay, let's see about direct band gaps semiconductor laser. Okay, uh, here principle and principle of pumping is okay. Okay, let's skim through this point. Electrons are injected from it. That is basically when it's forward bias. So when forward bias is given, the electrons travel from N to P and holes from P to N, right? So when these cross over, then their densities are high. Okay, so the radiative recombination of electrons in this conduction band with the holes leads to emission of light. So when these electrons from N type combines with the P type, it emits light of wavelength, which is the wavelength is inversely proportional to the band gap of the energy. Okay, band gap energy of that semiconductor. Okay, let's see. This is how the band gap of semiconductor presents. Okay, so P type and N type. So here, the the N type has is in a step lower than the P type, as you can see. But when the junction collides, that is when we do forward bias, right? So this junction collide comes. So the Fermi level gets above. Okay, so when this Fermi level gets above, it automatically creates a population inversion there. Okay, so Fermi level is basically the level where from where the electrons can present in an atom. So when this Fermi level is increased, the the population inversion is automatically achieved, and with that the stimulated emission can be done. Okay, so yeah, when current is injected into the active layer, the photons are generated through stimulated emission by yeah, this is the basic. So it's just basically the thing that we have studied earlier. So okay, let's see. This is the a basic of direct band gap and indirect band gap. So in direct band gap, the conduction band and valence band are in the same place, but in momentum, same momentum. But here it is in of different momentum. Okay, but that's not necessarily required here. But here P type and N type is given. Okay, that's basically in a semiconductor. And this P type and N type, that is the semiconductors are P type and N type are kept in this highly reflective cavity. So for the lasing action, you need two mirrors, right? So you are placing that in this cavity. Okay. Mm. So here basically you can see. So this explains pretty much everything. So here the depletion region is given between P and N type of the semiconductor. Okay. In this junction, you can see the Fermi level here is maintained below this EV. Okay, not in conduction band. Okay, so when this depletion region gets reduced, you can see that the N side has the Fermi level has gone upper, so that the electrons can be inverted. Population inversion can be achieved there. So from there, from N the from N side, the in P side, this holes and electrons get combined and it releases photon. So when this depletion region is reduced, the population inversion automatically happens. As you can see, when this population inversion is higher, so when the number of photons is sorry, when the number of electrons is higher in the above, then the population inversion happens. Then you can achieve the stimulated emission. So there are two types basically, homojunction and double heterojunction. Okay, so in homojunction it does only has one p and one n side, but here in double heterojunction it has the double p and double n side. So it just creates basically a higher energy gap and a stable one. I'm talking about the double heterojunction compared to homojunction. Okay, so it basically creates a second energy gap which helps to maintain a highly coherent pulse. Okay, energy pulse of the laser action. So this is how semiconductor laser works. So pretty much covers everything. So I guess this covers pretty much everything of laser. Yeah, thank you guys. Now it's not mute. Okay, mute.
Hello. Yeah, great. Uday here. We'll be starting quantum physics in 5 minutes. Yeah. So if you have some of your friends who want help with quantum physics, please tell them to come very quickly. I'm going to start. Yeah. So after quantum, we'll move on to semiconductors and its derivations, and we'll just see the first 2 units very shortly. Yeah. So that is the key idea of the session. I hope lasers was useful. We'll just move on to quantum and quickly complete it in some 40 minutes. We'll then move on to semiconductors another 40 minutes, and then we move on to the first two that will take together some 30 minutes. That's it. Okay.
Yeah, you're right.
Yeah. Is that clear? Can you all react? Can someone drop a text in the group that we are starting quantum physics?
இது ஆன்ல வச்சுக்கோ, தயவு செய்து இது ஆன்ல வச்சுக்கோ. ஓகே, எப்பவுமே ஆன்ல வச்சுக்கோ. மியூட்
Hello, hello, hello. Hello all. Thanks for joining in. We'll be starting in one more minute. Can people confirm if my voice is audible and screen is visible? Yeah. We'll be starting in 1 minute. Mic check, one, two, three. Yeah. Hello all. Thanks for joining in. We'll be starting this session now. I can see your chats and I can see your reactions. So please do feel free to put your things whenever you have some doubts, whenever you have some queries. I would then only I can understand whether you understood or not. Yeah. So please. So talking about quantum physics. Yeah. So the flow of the session will be: we have completed lasers. After lasers, we are doing quantum, and after that, we are doing semi. We are planning to complete these two in 1.5 hours. And after this, we have acoustics and ultrasonics and fiber optics. We are trying to complete both of these in another hour. So these two in one, these in 1.5. We are trying to complete it as soon as possible. Yeah, but don't hesitate to ask your doubts if and when you have anything, right? So yeah, talking about quantum physics. So what is the counterpart of quantum physics? It's what? Classical physics. What did classical physics assume? It assumed a lot of things which does not work in this tiny world, right? So quantum physics talks about minor behaviors in a very small scale that are not very useful in defining quantum scale properties, right? So we learn about how quantum physics fails. Classical physics fails in rise to the quantum physics. And we also learn about energy distributions. We learn about how Planck gave an expression for the energy density, and we learn about
Heisenberg's uncertainty principle. We learn about de Broglie's principles and stuff, and we also learn about one-dimensional potential wells. We learn about Schrodinger's equations. We learn about both time-dependent and time-independent equations, 3D box and density of states, and Fermi energy levels. And I think that's the end of it, right? So that is the flow of the session. Now, moving forward, firstly, UV catastrophe was one of the things which was the initial concept for teaching quantum physics, because it was a failure of classical physics, right? So according to classical physics, Rayleigh-Jeans law, or a lot of laws, right? In specific Rayleigh-Jeans law here, the energy density of the black body radiation is given by some expression like this. Okay, you need not memorize this expression as of now. We'll be seeing this anyways. Okay, so this energy density expression, which is given by classical physics, predicts that whenever you tend your frequency towards the infinity, okay, your energy density is going to be infinite. That's what your what says. This Rayleigh-Jeans law, according to the classical physics assumptions, right? So it says. So this seems to be what a catastrophe, because experiments showed. So experimentally this was not observed. Experimentally it was observed that energy drops to zero in the UV region. So classical theory predicted infinite energy, and this was one of the failures of classical physics. See, understand, whenever you have a theory, okay, it should be applicable to a general case, right? So that's what even when you're learning problems, you learn about some general cases and you apply it in specific cases only by taking some arbitrary constants and specific values, right? That's how you do problems. So they were fighting for getting a general case of reducing a problem for an energy density radiation from a black body. Okay, but they're not able to get it. So one thing utterly failed at lower frequency or higher wavelengths. Other one failed at lower wavelength or higher frequency, right? So they are not able to generalize that. Okay, and that was not able to generalize as a principle even today. They were only able to generalize as a hypothesis, and the hypothesis was given by Planck. What did Planck say? Planck said easily. What? Okay, energy is not going to be continuous. Let's just take it discrete. Come on. Yeah. So he gave that amazing thing, right? Energy is discrete. That's it, right? And he called energy going to be directly proportional to what? Your frequency. So E is equal to what? It's simply NHQ. Where H is going to be Planck's constant, 6.626 into 10 power minus 34 joules second. So that was the whole thing which was given by Planck. And because energy was assumed to be discrete, he added up things, he added up energies, distributions, he added up things, and he obtained an energy density expression, which was actually deduced to be what? Both Rayleigh-Jeans and one more, right? So we'll be seeing that throughout this. So let's see this. So I told you, right? There are few questions for which people are searching for answers, but all those questions were not answered by classical physics, so there was a need for quantum physics. Mr. Kirchhoff observed that for black bodies, energy is a function of temperature and frequency, but that function was not able to be deduced. And Stephen, he gave an expression that this energy, right, is going to be directly proportional to T power 4, energy per unit area per unit time, right? So Stephen gave that expression along with Boltzmann, Stephen Boltzmann's law, right? And this did not talk about radiation levels at any frequency. This was not, again, a generalized one. Again, so we are all talking about radiations from black bodies, energy radiated from black bodies, and so on, right? So what is a black body? A black body is a perfect emitter and absorber, right? So you can just visualize it as something like this: a spherical polished cavity, blackened inside and completely closed except for a narrow orifice. Now we know that classical theory assumes that energy is going to be what? Related to amplitude and not going to be with respect to frequency. Any charge radiates energy, and a large number of particles can occupy a given energy state, and energy is going to be what? Having a continuous range of energy, levels, right? That is what was observed by what? Classical theory. But we observed that it was not actually true, right? According to classical theory, radiation from a hotter body should have more UV rays than observed experimentally. We saw that, right? In UV catastrophe here, it assumed infinite things and all, but experimentally that was not the case, right? So that was also there. You see something like this. So this is talking about, again, Wien's law. Wien's law is nothing but the lambda which you have, the lambda is the wavelength, lambda max, okay, of the radiation will be inversely proportional to the temperature. right? Higher the wavelength, lower the temperature, and the other way around as well, right? So this confirms that lambda max into temperature will always be what? Constant. We call this constant as Wien's constant. I think it's 2.898 into 10 power minus 3, I guess, just like a meter Kelvin, right? So that's how it was, right? And according to classical thing, according to UV catastrophe principle itself, according to Rayleigh's law, if you observe, actually, here they have taken this with respect to wavelength. If this graph has to be with respect to frequency, it will be like this. It will be like this, okay? Because this wavelength inversely, right? So it will be like this. Okay, the graph will seem like this. Okay. So basically, it was assuming an infinite level of things, right? Whenever you increase frequency, the radiation which you observe is actually infinite, according to classical, right? But that was not actually the case. The actual case was that it goes to this particular thing and then it turns around and gets back. Right? So this was the deduced one according to the experiments, and this was actually proven by what? Planck's radiation law. Okay, so just understand that. I think that should be the thing. So as temperature increases, energy at each wavelength increases. Wavelength at which maximum energy is emitted decreases. Okay, so total energy at a given temperature will be proportional to what? T power m. So even there we saw, right? Energy is proportional to T power 4 in Stephen Boltzmann law. So the total energy at given temperature is going to be proportional to T power m. And yeah, so that is there. Now Wien, so this is just history things which you have to just note. Okay, I'll be doing the derivations in a while. So yeah, Wien gave an expression for energy. So what was the expression which Wien gave? Someone C1 lambda power minus 5 e power minus C2 by lambda t kt or something like this, right? So lambda t. So that was the expression which was given by Wien. And this was what? This is not true for longer wavelengths. Only short wavelengths are applicable, right? And this was given by Wien. And Rayleigh jeans came up with the distribution which miserably failed at shorter, okay, but was working for longer. So they're not able to generalize this thing, right? So Rubens discusses with Max Planck. With Haas, Planck has equation but no theoretical explanation for it, right? So what happened? He gave a theory. Wow, nice. Let's come on. Let's just take energy equal to discrete. That's what. And when we ask for proof, they will say this. Experience will prove whether this hypothesis is realized in nature. That was a nice statement. Anyways, so yeah. Again, we used various things to measure Planck's constant as well. One of those experiments which you do in your lab, right? Have a photoelectric effect and a lot more, right? So let's just do this derivation quickly. So energy is going to be what? Discrete. So energy is just NH nu, right? So let's just read this area out, nothing much. So each radiation is modeled as what? Tiny oscillators is going to be present in each radiation. And each atom is modeled as a harmonic oscillator, each one just jingling, right? Higher the energy, larger the speed of the oscillation and further displacement. So frequency, so we know it, right? So frequency, if it's going to be higher, automatically energy becomes higher, right? And yeah, higher amplitude. So Planck's hypothesis said that energy of each oscillator is not continuous but discrete. It can take values with a multiples of its natural frequency. We know all this. Therefore, radiation of bound cavity can be modeled as emissions from a collection of infinite number of oscillators. We have a system of large number of finite oscillators, each starting from a different energy, distinct energy levels. So there will be distinct energy levels, each carrying separate energies. You add up, there will be infinite energy levels like this. That's it, right? So that was the whole thing. Now we have to find the total energy density radiating the frequency range between nu and nu plus nu. So see, you have to find the total energy. How can you find the total energy? Find average energy. Okay. Average energy of each oscillator. Okay. And multiply by what? The total number of oscillators. I'll give you, one oscillator, what is the average? Multiply by how many oscillators are there? With the total energy of all the oscillators, right? In radiation in specific, between frequency range, right? So that was the whole idea. Okay. Again, for finding the average number of oscillators itself, you have something which you deduce. Okay. So firstly, average number of each oscillator will be taken as what? Total energy divided by number of oscillators. Again, we might ask, we are actually interested in finding total energy. What is the point of this? So there are variables which might not be very much useful in our formulas. So we are not using that formula. We will experimentally deduce and not part of the syllabus in finding few things, the number of oscillators for specific. We'll be seeing that in a while. Okay. But let's just get the formula for average energy of each oscillator. What is that going to be? Total energy by number of oscillators. First, let's deduce a formula for number of oscillators. What is the total number of oscillators going to be? The total number of oscillators will be nothing but what are the oscillators available in each level. So first understand this formula. This formula does not have any derivation for you. Okay. The number of oscillators in the ith energy level, right, is given by the formula n naught e power minus ei by kt. Okay. So n is the number of oscillators in the ith energy level. N naught is the number of oscillators in the ground level. EA is the energy of the ith level, right? EA is nothing but IH nu. You know that, right? So that was the thing. So this is the formula which generalize the number of oscillators in the ith level. What are you interested in? You are interested in finding the number of total number of oscillators. So total number of oscillators will be given by the formula. First, what is the number of oscillators in the ground level? N naught plus what is the number of oscillators in the first energy level? N naught into e power minus E1. What is that? H nu by kt. Plus second level n naught e power minus 2h nu by kt, right? And then n naught e power minus 3h nu by kt, and so on, right? So what happens? You can take few constants out. I also see something e power h nu by kt is going to be repeating. So what I'll take is e power minus h nu by kt. I can just take it as what? X, right? So what happens here? N naught plus n naught into x plus n naught into x square plus n naught into x cube, and so on, right? We can take n naught common. What happens? 1 plus x square, and so on. What is this? This is a beautiful arithmetic sequence, geometric sequence, right? So what is that? This is a simple geometric infinite GP. So 1 by 1 minus x is the formula for it. Okay. So n naught by 1 minus x is the expression which we deduced for what? The number of oscillators. So the total number of oscillators. Now we have to deduce the total energy of all the oscillators collectively, and we can just divide it, right? So what is the total energy of all the oscillators? Firstly, how can you do that? So till this point, is everyone here? Can you please react with a thumbs up or just put something in the chat? Yeah. All of you please react. Can all of you please react? Okay. So what is the energy or total energy of all the oscillators going to be? It will be thank you. It will be what? What is the number of oscillators in the ground level multiplied by what is the energy of the ground level? 0 plus what is the number of oscillators in the first level multiplied by what is the energy of the first level? What is that? H nu plus n2 into 2h nu plus n3 into 3h nu, and so on, right? So this n0 into 0 will be just 0 plus n1. We just deduced it. What was n1? n0 into e power minus h nu by kt. That's what we got, right? So basically that was nothing but n0 into x. So this was n0 into x plus n0 into x into h nu plus n2 would be n0 into x square into 2h nu, and n3 into 3h nu will be there in this expression. So this just keep going on. You have to put dot 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 dot. Okay. So n3 into 3h nu. So what happens? You will just get n0 into x cube multiplied by 3h nu. So let's try to take the commons out. Okay. So can somebody please confirm if the live stream is working perfectly? If all my voice and whatever is in the screen in Gmail is it getting presented in the live stream in YouTube? Can you please check it? If one of you. Yeah, if it is going to, please check it in the YouTube. One of you please check it and put a chat here. Yeah, I'm just taking the comment in the meanwhile. Okay, so we'll just take what? We'll take the common of n naught x and h nu, right? What happens? N naught x h nu will be just 1 plus n naught h nu and x. So there will be one more 2, and there is 1x, and then n naught h nu and 1x. So 3 into x square. So it just keeps on going, right? So what happens here? N naught into x into h nu into 1 plus 2x plus 3x square plus 4x cube plus 5x power 4. What is this sequence? We have seen this. This is quite familiar. Yeah. Thank you. Right? I hope the voice is also visible. Voice audible and the screen is also visible. Right? So 1 plus 2x plus 3x and so on. So this will be nothing but what? An AGP. You know, right? So we have seen the given expression in mathematics also. So 1 by 1 minus x whole square. Right? So that was the expression which we deduced. So for convenience, I see this somewhere. So I have seen this formula somewhere. What is that? I have seen n naught by 1 minus x somewhere. And I'll write the remaining here. H nu by 1 minus x. Right? So what happens? N naught by 1 minus x was nothing but the total number of oscillators. Now x nu by 1 minus x would be nothing but what? Easily average of each oscillator, because this was total energy expression. Right? So I got my easy answer for average of each oscillator. Which is nothing but what? X nu by 1 minus x. Right? So for convenience, I just divide by x. So what happens? H nu by x minus 1. Right? So x inverse minus 1. I have divided the whole equation by x in numerator and denominator. So what happens? H nu by x inverse minus 1. Why did that? Because x was negative. E power minus h nu by kt. Now it becomes e power plus h nu by kt. So I substitute by e power plus h nu by kt minus 1. Easily, right? So this was the average energy of each oscillator. Easily we derive that. Now we have to find the total energy. Now what was the total energy we observed? Total energy was nothing but the average energy of each oscillator multiplied by total number of oscillators. Now we derived that total number of oscillators was n0 by 1 minus x, but that was not so meaningful. It was experimentally observed meaningfully. We are not going into it. So let's just take it as 8. So just take this formula, 8 pi nu square by c cube into d nu. So this was the one which was deduced by the experiments in finding the total number of oscillators lying between the frequency range nu and nu plus d nu. Okay. Now what was this expression? Average energy of each oscillator is the same thing, which is nothing but what? H nu by e power h nu by kt minus 1. Okay. So this is what we have. So let's just multiply things together. So what do you get? 8 pi h nu cube by c cube into 1 by e power h nu by kt minus 1 into d nu. So this is what we have. So let's just cross check if the expression is right. So we have 8 pi nu square. So you can write it in either ways, right? So 8 pi h nu cube by c cube, h nu cube by c cube, 1 by 1 by, okay, sorry. Yeah, 1 by e power h nu by kt minus 1. Okay, it's right only. Right? So this is the formula which was given by Planck. Very nice formula he has given for total energy formula, right? So again, this formula, so what was that thing? Anyone can give formula, right? Mr. Vine also gave formula. Mr. Ray also gave formula. But how is the formula validated? You'll have to check it if it is experimentally true or mathematically true for all the cases of frequencies and wavelengths, right? So that's what you know. The frequency is what? F is equal to f lambda, you know, frequency and wavelength are inversely proportional, right? Sorry, B is equal to f into lambda, right? So B in specific is C. Okay. So what happens here? You have to cross check if this has to be true for all the wavelengths or frequencies. So what I'll do is I'll just plug it in. So I'll just show you here. I'm not writing it. So this is the formula which we derived. Okay. So this is the formula which we derived. And for shorter wavelengths and longer wavelengths, how is it going to be true? So for shorter wavelengths, what happens? You can take e power h nu by kt as what? Because it is going to be a shorter wavelength, frequency is going to be higher. If frequency is higher, e power this thing is higher. So subtracting 1 does not make any big difference. So let's just take it as e power h nu by kt alone, not minus 1. Okay. So that becomes what? If it goes to numerator, e power kt by h nu, right? So that will be there. So you can just take what you have d nu here. You have to put it in all terms. So you're defining everything in terms of lambda. Put it in lambda itself. So put nu as what? C by lambda, and you can substitute as d nu as what? Minus c by lambda square d lambda, and because it is going to be positive only, c by lambda square and d lambda. Okay, so you can substitute d nu as what? C by lambda square and d lambda. You can substitute nu as what? C by lambda. You can substitute e power h by kt as what? Minus 1 as what? E power h by kt only, right? And you can cancel out whatever c's and lambdas you get, and you'll get this final expression, which resembles the original expression we had there for Wiens, right? What was that? C1 lambda power minus I, e power minus e power lambda d lambda. The exact same expression we will get here. C1 and C2 constants were also found. Okay, so that was the whole point of what? Applicability of what expression? Planck's expression in terms of shorter wavelengths. What happens for longer wavelengths? This is not the derivation was only till here. Okay, this is just validation. Okay, if they ask you to validate it, you can do it. Okay, so for longer wavelengths, what happens? If it's going to be a longer wavelength, the frequency is going to be lesser. If the frequency is going to be lesser, e power some lesser quantity is going to be returning only very less thing. You remember in the mathematics we learned Taylor series or not, in which we derive e power x is equal to 1 plus x plus x square by 2 factorial x cube by 3 factorial and so on, right? If this x is going to be lesser, all these quantities still is going to be what? Negligible only. There is no need of considering that. So you can round it off. When x is going to be very lesser, you can tell e power x is nothing but just 1 plus x, right? So e power x by kt is 1 plus x by kt. You can substitute this section as 1 plus x by kt. So whenever you are validating, you start from the original formula, you will see the condition. Based on the condition, you will validate it. You will put everything in the same terms and you will cross check with the Rayleigh's or Wien, right? So 1 plus x by kt minus 1, 1 cancels out. It just comes to numerator. Again, the same thing, you will substitute as what? C by lambda. D nu as what? C by lambda square. So modulus, right? D lambda. And you just substitute it, and you can put nu is equal to C by lambda. There cancelling will be there. Okay. So this is what you'll get. You'll get 8 pi kT by lambda power 4. I have seen this somewhere. Where is it? We have seen this somewhere in fiber optics. Remember this in fiber optics when we were learning about losses and all, we were learning about energy. It was actually the loss was actually electric potential to inversely proportional to lambda power 4. Rayleigh scattering there, we've seen that, right, somewhere. We even saw a graph something like this in which we had absorption spectrum and all, right? Means HUO minus absorption peak was there and so on, right? So again, that was inversely proportional because lambda power 4, right? So that was again Rayleigh scattering only. That was also proved by what? Planck. Easily. Simple derivation, please make a note of that, right? So UV catastrophe, according to classical theory, radiation from a hot body should have more UV rays than observed experimentally. So classical theory failed. Energy was discrete, not continuous. It was observed experimentally that energy at each wavelength increases. Wavelength at which, as temperature increases, energy at each wavelength increases, and the wavelength at maximum energy is emitted decreases, right? This was again something related to Wien's law again. Wien's law talks about displacement of the gas, right? So you increase as long as you increase your temperatures, your wavelength decreases. That is also there, right? And the total energy at a given temperature is proportional to T power m. That also we saw. Right? So Max Planck gave us this formula. We have seen this. We have seen the expressions for Wien's radiation law. We have seen the expression for Planck's distribution, which generalized the Wien's law as well as what? Rayleigh's law. Right? We have made various applications here. You can just take a note of all those applications. Just line theory. Okay. And here you have a formula. I'll just tell you the approach to solving that. The ratio of the energy density of the radiation at this frequency is observed at a higher temperature TH to that recorded at this particular level. We have to find what TH. That's it. You have to substitute your Planck's formula for both the cases. That's it. Okay. For the first case, what is the formula? 8 by h nu q by c q 1 by e by h nu by k instead of t th minus 1 d nu. The same formula. Now instead of th, you will put 300 here, right? Now the ratio, you will just cancel out all the constants will go off. You will have this expression coming to the numerator, this expression coming to the denominator because 1 by 2, right? So equals to 1 by 2. So this comes out. Now you have this expression. This is equal to this. Okay. Now what can you do? You can just take logarithm. Logarithm of this is equal to logarithm of this because log of a by b is nothing but log a minus log b. You can do that. Now you can take log a by log b. Now you can take common here. So e per h by k is common and h by k is constant is given by question. So let me substitute that. So this value I know log of something. Okay. I have a calculator. I can find the log of something. Now this you have. Now in the right hand side we have ln of e power. So intentionally I want it to be e power so that e and ln cancels out. So actually by k I took it common. We have 1 by 300 minus 1 by th. ln cancels out. So we just have what h by k into this thing. And you can easily cancel out. You can easily find th here. h by k, you know, this all these things you can know. You can just evaluate for h. That's it. Okay. So that's always there. Okay. Again, I'm not sure the solution for this problem is not given. I think you have to use Stephen Boltzmann law. Just go through this formula. If you have any doubts, tell me. You have to use, I think, E is equal to sigma t power 4. Okay. So from a particular point, you are observing something. You have to calculate distances and stuff like this. As of now, we are not concentrating on this. Now, just take a look at this whenever you get time. Yeah. Now, moving forward. We have a spoiler here. We'll be coming to the spoiler lastly, but yeah. Okay, so that is the thing is. So till this video has any doubt, okay, we'll be brushing up things, anyways. So till this point, any queries, can all of you please react? Thumbs up, please. Only one is react. Yeah. Okay, all right. So we're moving forward. Only if you react, you'll know whether you understand it or not. Otherwise, I'll repeat it. Okay. Please do react whenever you have something, or whenever I ask something at least. Okay. So yeah. Otherwise, I don't have interest to teach. Please. Okay. So yeah. Talking about the next one. This is very simple, guys. So de Broglie's hypothesis. All you have to remember. Your matter has both things, wave and particle natures, do not occur the same things. Different experiments show different kind of natures, but both natures do not exist simultaneously. Right? Wave particle duality is exhibited by we told for a wave, a particle could be there, and a particle wave could also be associated with given by de Broglie. right? What was the formula he gave? He told that the wavelength of that particular particle which you are telling that wave exists, that wavelength is but what? Inversely proportional to what? The momentum. So lambda is inversely proportional to p. So this proportional. One second. Yeah, is my screen visible, guys? Okay. Yeah, great. So we'll move forward. Uh, we know that lambda is what is directly proportional to 1 by p or inversely proportional to the momentum itself, right? So we know what is the constant lambda is equal to h by p, right? So we can write it as what? H by p. P is nothing but mv. So we can write p as mv, and we know that p can also be written in terms of kinetic energy, which is root of 2mk. Okay, and one second, guys. One second. There's a problem with the live stream. One second. Can someone of you check and tell me if the live stream is going properly? I don't think it is. One second. Oh, great. So, we know that h by root 2 mk is also there. So, you know that kinetic energy for gases can be regarded in one special case as 3 by 2 kT. So, it's by root of 2m. K can be written as 3 by 2 kT. Okay, so 2 can get cancelled. We have a formula root of 3m kT. Okay, that is also there, right? And just a few formulas. Okay, both are considered. Yeah. So this is there for you can also put it in terms of voltage. In voltage, it will be nothing but what? For an electron in specific, it is 12.27 by root v. Okay. You can define your K as what? Q into V. K is in terms of the energy is nothing but what? Voltage related charge. Right? So you can do that as well. And you can substitute the values of for an electron, you get this formula for the lambda. Okay? Direct formula, nothing else. I'm not emphasizing more on this, just blind theory. Okay? You just have to know this formula. Particle is associated with the wave, we call it matter wave. And we have defined the formula. How did we take this formula, by the way? Benefits of both the things have to be same if they are same. Right? So MC square is equal to what? MC square for what? A particle. For a wave, what is the energy? For a wave, the energy is given by what? The formula h nu or hc by lambda. Right? So we just put hc by lambda here. Hc by lambda. You can take c cancels. Now lambda will be nothing but h by mc, and that is mv, which is p. So h by p and so on, right? So that's how you derive it, right? And there's also something like your angular momentum is going to be quantized. Just a pure concept around your energy levels. The angular momentum is going to be what? In an integral multiple of what? Your what is that? What is it? H bar. Or we will just derive this one. Let's say. So what is the circumference of this? The circumference. So it was all observed here. The circumference when you have n is equal to 1 or whatever into lambda. It was always in integral multiple of the wavelength. So 2 pi is equal to n lambda. So r is equal to n lambda by 2 pi. You know not lambda is equal to h by p. Just substitute it, and h by 2 pi p. You know p is mv. Just substitute that also. And you have a weird quality of clubbing h and 2 pi together because it was always together. So you always put what? H by 2 pi as h cross, h bar, whatever, right? So from here till the end of this, we'll be using h cross. Okay, so h cross means h by 2 pi. Okay, so h cross by mv. Okay, so you will easily see that this is for r. So r is equal to h cross by mv. So technically MBR is the angular momentum. So MBR is nothing but n cross. You easily see that angular momentum is what? Quantized. Right? So that was also there. And when will which nature dominate? And the distances which you are looking for, right? The principles where you are applying, where you are going to be looking for, is going to be very comparable to your photon's wavelength, right? Then it's purely wave optics. If it's going to be somewhere around the de Broglie wavelength of the particle, okay, then it is purely wave mechanics, quantum mechanics, right? if it's going to be far greater than the length of the photon, geometric optics, basically light theory which we learned in our 12th. And if it's going to be far greater than de Broglie wavelength, it is going to be classical mechanics. Okay, so that is the whole idea here. Okay. And how do you associate a wave and a particle together? You call it a wave packet. A wave packet is something which encloses both wave nature and particle nature. You put a lot of waves into something, you localize it in a space, you call it a wave, but particle. Okay, I mean it is localized the particle, but it has a wave distance, so it will be called as what? Wave packet. Cool name, no? Nice. Yeah. So how do you construct it? You put a lot of waves and club it together to make a wave packet. A lot of waves are superimposed, right? So a lot of waves are put together, right? Again, these expressions, just know the formulas. Okay, not too much of things. Okay. So what is the thing? The wave. So what is this thing? You know that. So this is just few derivatives because it is there and then deriving it. So just know the formulas. Yeah. Whenever something is asked, write something. Write some formulas at least. When whatever quantity is going to be there, for you to link two or three things, you can understand these formulas. That's why. Okay. So what is the velocity? You know that velocity is always what? Angular velocity by angular wave number, right? So k is what? Angular wave number. So v is equal to omega by k. We know that. Okay. And what was E? E was nothing but h into nu. H into nu. And you know that nu was what? Nu was omega by 2 pi. You know that, right? Omega similarly, you can also deduce it by what formula here. Because it is going to be E by P, E is nothing but what? MC square for the particle, right? And what P is going to be nothing but the momentum, MB. So technically it is C square by B. And when B is very, very comparable to C, both of them become just C. This is going to be the velocity. But generalizing just keep it as C square by B, right? After MB square. In order to make momentum here, what am I doing? I am multiplying and dividing it by what? M. Multiplying and dividing by M. So half into M square B square by M. What is MB? MB is P. So P square by M. So this is going to be K. So P square is what? 2MK. So that's the whole idea here, right? So we are just substituting what? P square by 2M. Because 2M is going to constant, it will come out. P square is respect to P nothing but 2P. So 2 cancels out, we just have P by M. Which we clearly know what? V is nothing but P by M. Okay. And that P by M is nothing but V. So technically, what are we trying to convey? We are trying to convey one specific thing. For matter waves, group velocity is the particle velocity itself. For matter waves, group velocity is the particle velocity itself. Just remember that. That should be there. I think, yeah. So you can just do these things to 12.27 by Ruby formula. And yeah. I'll tell people to do it for semiconductors. Sure. Okay. So yeah. So till this point, anyone has any doubt? We are moving on to the golden aspect of this chapter. Yeah. Okay. So this is going to be interesting. Yeah. So what happens here? We have to reduce an expression for something that we have been not reduced for. So we want to reduce an expression for something that does not even exist really. Yeah. That was the whole point of this. So this is very interesting. Trust me. So firstly, what are we talking about? We are talking about something called wave function. Okay. What is a wave function? A wave function is a function that talks about the wave. Okay. So basically, this is something that gives all the information about the wave. Okay. So you're talking about anything in this world. Okay. You're talking about anything. Okay. You associate a wave function to that. Okay. Comparable to quantum mechanics principles. Okay. So you associate anything. Okay. With the wave description. Okay. In such a way that your wave function should determine all the aspects of that particular wave. Okay. So wave function is a beautiful aspect here. It's a complex function. Understand that there are going to be ioters here. Okay. How do you define a wave in general? a simple wave, which is y is equal to how do you make waves? Just put one amplitude, put one sine or cos function, put one omega t minus k, or kx minus omega t, whatever, right? Omega was angle frequency, gives time, gives angle number, x position, right? So this is how you generally define a wave, right? But here, how are you defining it? Again, we define it like that only, but this is not going to be a sine or cos function. We'll be looking at in the future why it is not, but it is going to be an exponential function. Okay. So what is that supposed to be? This is by psi. Okay. Psi. So this has an amplitude A, an exponential function E, and B convention let's use it as minus iota, and B defines something called omega t minus kx. Okay. So omega psi was defined as what? A per minus iota, omega t minus kx. This does not come in derivation. I'll tell you when derivation starts. Okay. So this was I'm telling you, I'm putting this for you to understand stuff. Okay. Now what is this? Omega. So again, weird quality. What is my weird quality? Check out h and 2 pi together. H and 2 pi are hidden. Okay. So what you do again? Firstly, why am I doing this? Not weird quality. So you want to all the information that particular wave in the wave function equation. So you want to put energies and all those stuff into your wave function. So that's why you define it in that terms, right? So what happens here? You know what? Omega is nothing but E by. So we know that omega is h nu. Okay, we derive that. So what is that? E by h cross. What was that? One sec. Bro. Omega was E by h cross. K was P by h cross. So let's just put that here. Omega was E by h cross, and K was P by h cross. H cross will take common. So E per minus iota by h cross by E t minus Px. As simple as that. This is where the derivation starts. You're going to derive two cases, time independence Schrödinger's equation. So what do you mean by that? You're considering the case of time stuff. So omega is equal to A minus iota by h cross E t minus. So we can take this as two aspects. We can take a function of t, and we can take a function of x also. How are they defining it? 1 second. They're defining it as function of t and function of x. So in both cases, if you try to reduce the expression for a time independent, wave functions form, whether you take it from this very small positions, okay, or you take it from the entire thing also, the answer for psi will give you the same, okay. So that is the whole aspect of time independence Schrödinger's equation. So what am I saying here? I can just take equation as a function of one side and question another side. So A per something will be there minus E I by h cross. And here I have A by minus I by x by h cross. So this was function of t, this was function of x. So irrespective of that my wave function gives you in time independent. Okay. Some theory. So again, Heisenberg's uncertainty principle. You cannot measure position and the momentum of a particle simultaneously. So del x will always be greater than h by 4 pi. I'm very used to h by 4 pi. H cross by 2, right? So this is the whole idea. You cannot. Right? So when the error of one thing is going to be higher, the next one has to be compensating for it. So classically, the state of particle is well defined. It can specify its momentum and its time. Classically, a wave is well defined when you can specify amplitude and phase, right? Uncertain principle says both of the position momentum cannot be measured simultaneously. So as per quantum mechanics, wave particle duality, you cannot simultaneously specify position and can only talk in terms of what? Probability. That was the keyword there. Okay, you can only specify a fuzzy state function. Okay, you can only specify what? Fuzzy state function that captures the set of continuous probabilities, chances. I will always talk about what? Probability. So in quantum mechanics, object is represented by a wave function. That has all pertinent information. One second, please. Yeah, yeah, okay, okay. Yeah, yeah. So what happens? You only talk about probabilities and possibilities, right? So a wave function has all the pertinent information regarding the state of it. Time evaluation is how one thing changes temporally with respect to time, right? Heisenberg looked at energy as an observable and representative matrices. Okay. Scratching the wave formulation from the classical representation. That does everything. Okay. Anyways, so the whole derivation will do it now. Okay. So what is psi? The expression which we deduce for psi is psi is equal to a e power minus iota by h cross into et minus px. So what happens? 1 second, guys. There is some trouble with this. Partial derivatives with respect to whom? With respect to position. So those psi, nice word. Those psi by those is equal to what? What is that going to be? All the, you know this is an e power x function. All the coefficients of x will come, right? E power x derivative is a into e power x. So we'll just take that out. So whatever is going to be the coefficient of x. What is the coefficient of x? Minus iota h by h cross into minus p. So that is going to be p iota by h cross into something. What is that? The hereditary function repeats itself, right? Because we know it. E power x thing, e power x is x into e power x, right? So pi by h cross into psi. This is what we got for dou psi by dou x. Now let's differentiate again. Dou square psi by dou x square. What is that? Going to be? This is just a constant. Leave it as it is. Again, the derivative is the same, right? Pi by h cross again psi will come out, right? So what is that? So what is that supposed to be? What? P square. What is I square? Minus one, right? Because I minus root of minus 1 by h cross square into psi. So this is what we have. Dou square psi by dou square. Again, this does not give me all the information I need, right? I want all the information. So what am I doing? P square is 2mk. That's what we derived. Kinetic energy. And kinetic energy is total energy minus potential energy. E minus B. So I can just substitute this expression there. So minus P square can be substituted as 2m into E minus B into psi already there. H cross square already there. This is what dou square psi by dou x square. Easily. Now moving forward with this. 1 second, I'll change color. This is not visible. And also format background. Yeah. Sorry. Yeah, right. So we got this expression. Dou square psi by dou x square is equal to minus 2m into e minus b psi by h cross square. So let's just take this that side. What are we interested in? We are only interested in keeping energy expressions, right? So we will just take this constant that side. Just multiply in the reverse order here. So it will be minus h cross square by 2m into dou square psi by dou x square is equal to E psi minus V psi. We just take V psi that side. We are only deducing E psi. So what is E psi? E psi would be V psi plus minus h cross square by 2m into dou square psi by dou square. You see this somewhere. Energy, total energy, potential energy. So what is this supposed to be? This is supposed to be kinetic energy, right? Kinetic energy, right? So this talks about something. Okay. So there is a concept called eigenvalues, eigenvectors. We'll be learning that in the third semester, I believe. Okay. So what is that? An eigenvalue, eigenvector is nothing but you have. So that we will learn it in the concept of matrices only. So that says whenever you have a matrix A, okay, you are multiplying that by a vector x, let's say, that is going to be what? A value multiplied by the same vector x. So ax is equal to lambda x is the formula actually. So you have a matrix A, you multiply by a vector x, that will result as the same vector x multiplied by some constant only, that is lambda. So you call this lambda as eigenvalue, you call this x as eigenvector. Okay, so that is the whole point here. A is just a matrix. In this context, why am I telling this? Why am I telling this? Okay, so we actually reduce the formula. I think. Okay, we'll see the slides now. So what happens? We reduce the formula something like this. So initially, when we did the first order derivative, partial derivative, those side with those, what did we get? We got this IP by x cross into psi of x, right? So this is what we got. Now you observe this one thing actually. You can take I by P separately. So here it will be H by I, those side with those is equal to P psi. Essentially, P psi is nothing but momentum. But P is momentum. Okay, psi is just a wave function. Now H by I into those side by those x is talking about some operator. Now understand, psi is repeating both ways. Here also psi is there, here also psi is there. So psi is going to be the vector which I talked about there. Right? Psi is going to be the vector I'm talking about that. Psi is going to be that. And what is this? This is the operator I'm talking about here. Operator. You're operating what? You're operating H by I into dou by dou x. You're operating H by I into dou by dou x. Right? And psi is going to be the vector and P is going to be the eigenvalue. Right? So you call psi as eigenfunction, right? Or eigenvector, and P is going to be what? The eigenvalue. Right? So why am I telling this? Again, see, you remember I told you the context where you have exponential functions and wave functions. Why? Because when you try to differentiate it, you'll always get an exponential functions, right? That gate is a very resistant gate. That gate does not get integrated, does not get differentiated, right? He repeats himself whenever you do it, right? So what happens here? He actually gives the same guy in reducing the formulas for momentums or a lot of things we'll see, right? So whenever you're asked to find the wavelength, so wave function, whenever you're asked to find the momentum, okay, what do? You have to find the momentum, but I know the formula. What is the formula? H by I into dou psi by dou x is equal to what? P psi. So I can just simply operate H by I into dou by dou x on my psi. I can easily get P psi. I know what psi is. I can just take P. Right? Psi will just repeat itself. Right? So that was the whole concept here. Eigenvalues and eigenfunctions. So H cross by I. Sorry, H cross. Right? H cross by I, those psi by those would be P psi, and they'll be giving me a psi. I can just operate H by dou x on psi to get my momentum P. Right? So that was the whole concept here. Just concept, not part of derivation. Okay. Now I did this for one dimension because we assumed that it was just x. So this was the formula which we got minus h cross square by 2 dou square psi by dou x square plus p psi is equal to e psi. Now you can just extend this to all dimensions. So let's just take psi common. So minus h cross square by 2 dou square by dou x square will be there. Psi common, no? Plus v into this. So this becomes an entire operator in itself on psi. Okay, this is equal to e psi. Let's just extend it to all dimensions. So this becomes dou square by dou x square plus dou square by dou x square plus dou square by dou z square. Remember what operator this is? This is Laplacian operator, which we call as del square, right? So Laplacian operator, right? So let's just take that minus h cross square by 2 Laplace operator plus v whole multiplied by psi is equal to e psi. Now this whole thing, you call it as h. You will never see something. You will never learn quantum physics without seeing this formula somewhere, right? H psi is equal to e psi. Okay, so wherever you see about quantum physics, something, right? Science, whatever, you always see this in the frame. H psi is equal to e psi is always there. Scratches are always placed inside. So H is equal to E psi, where H is an Hamilton operator, which corresponds to this whole thing. Okay. So time independence of the equation clear for everyone. Can you please react? Okay, guys, if your friends have something, please tell them to join. Okay. Yeah. So now we are moving on to time dependence on this equation. Again, in that case, I have to consider time dependence also. So in that case, I have to take differential time also. So what happens? What is my sign? Psi is equal to a path minus I by x cross into et minus px. Now let's differentiate right differential to t. So those side by dou t would be nothing but what? T's constant will come out. What are these constants? These constants will be nothing but minus. So minus was there. Iota e by x cross into the same function, right? Same function. Now let's try to take things to the other side. So what happens? Because I'm interested in only finding e psi. Energy as a function of what? Time, right? So what happens? This would be just minus h by e dou psi by dou t. Every time we see dou psi, it feels nice. Okay. So what happens? I can just cancel things out. So minus 1 is just I square. Remember I square is minus 1. So I can just square I cancel out. Okay. So what happens? E psi is nothing but I cross dou psi by dou t. That's it, guys. You can just substitute in the time independence equation because we are time independent case. So what was my equation there? Minus h cross square by 2m dou square psi by dou x square psi as a function of x and t here plus b as a function of x and t here multiplied by psi as a function of x and t here. One second. Yeah. X and t here is equal to psi, but psi I just derived h cross square into dou psi. That's it, guys. This is the time dependence coordination. Okay. So this is what you have to remember for this particular slide. So just some theory. In case of particle moving in a force field characterized by a potential energy, here we consider if there are no dissipative process leading to energy loss, but the momentum will fluctuate. So that's why you are trying to kinetic energy in terms of p square by 2m, but not potential. We are not interested. So p square by 2m. Right, so plus v psi is equal to E psi, and we also derived an expression for the dependent case also, in which we replace E psi as what? IS cross dou psi by dou t. So physical very physical significance of psi. So wave function is a complex function. By the way, those who stay till the end, I have few things to tell. Stay till the end. So stay till the end. I have end of the chapter. I might say also end of the all the units. I might right. So wave function is a complex function that contains complete information. There are chances that may not come in the information of the state of the particle at any particular time and location. What happens? So you know what it contains everything. All the information of the particle at any time location stuff. It's a complex. You have to remember few properties of a single value. What is that? A particle cannot exist. Either I have to be here, or I have to be here, or I have to be in one of your rooms. There are no possibilities that I may be somewhere else. So there are no possibilities that I may be in one place. Right. So next single values. Next, continuous. I cannot be. I have to be exist. I cannot exist. I cannot exist. T is equal to 0. I can exist. T is equal to 0. I can exist. T is equal to 1. That is not the case. In the entire. That is not the case. In the entire. Continuous should also be there. So single value. Yes. First derivative should exist. So we define the wave function. The first derivative should also know. That you should also know that it should what? Be square integrable. Very important. Square important. Square integrable. You search the wave function of the universe. Okay. The universe. Okay. Search that throughout the universe. So initially we talked about wave function possibilities. That was the whole thing. How is that written? You take the wave function. You multiply by the conjugate. Meaning a plus iota meaning the conjugate of a minus iota. So you multiply by and integrate from the universe. Minus universe. You should get what? 1. You should get what? 1. So minus infinity to plus infinity. So minus infinity to plus infinity. Psi star what? 1. Should give you what? Finite value. In general, finite value, not be infinite. So that is also there. So that is also there. 1 second. Okay. I think so. It is still glitching. Okay. Yeah. Let's move forward. We know that minus infinity plus infinity. Psi star is equal to what? 1. Psi star is equal to what? 1. So square integral property has to be satisfied. So let's just go through this. And psi star is given by mod z star. Z bar is mod z. So similarly. So remember represents the probability of removing a particle in a certain particle. You can put whatever for reducing the probability in that particular interval. Okay. The wave function has to be finite. exists, it should be continuous.
And this is the normalization
this is the normalization condition
Any linear combination wave
Any
function
linear
also allowed
combination
state
wave
of the
function is
particle.
also allowed state of the particle.
All observers related to quantum mechanics
all observers related to quantum
operation of
mechanics
suitable linear operators.
operation of suitable
Linear as
linear
in alpha
operators.
beta multiplied
Linear
together,
as in alpha
right?
beta multiplied
So,
together. Right?
time independence conjugation represents the quantum mechanical equivalent of I forgot to tell you that. We had to tell you that kind plus potential is equal to total. That was the quantum mechanical equivalent of conservation of mechanical energy.
Conservation of mechanical energy.
That's what we derived. So we first derived the expression for wave function. How do we see it? We learned about the physical significance of it. We then learned p square by 2 1 plus p is equal to e. We substituted that. This was a classical equation. We substituted that. We realized that the quantum mechanical equivalent. So one dimensional time independent things.
So
which of these are acceptable wave functions? What can infer regarding uncertain position momentum? Now again, I think this is not possible.
I think
This
this
too
is
can
not
be
possible.
possible. Just check
This
it
too
out.
can be possible.
See if you have any
Just check it
doubt.
out. See if
Just
you have any
consider
doubt.
the
Just consider
properties.
the
Single value,
properties.
finite, continuous,
Single
and
value, finite,
further
continuous,
derivations
and
exist.
further
Doubts about
derivations
x1
exist.
x2, but yeah,
And
these
doubts
things are
about
valid, I
x1
guess.
x2, but
Yeah.
these things
So
are
yeah,
valid, I guess.
that is true.
Yeah.
I mean,
So
this
yeah,
is localized
that
in a
is true.
particular point.
I mean,
That's
this
it.
is localized in a
This is
particular
localized.
point.
I
That's
think
it.
that can also
This
be
is localized. I
possible,
think
maybe.
that can also
Okay.
be possible.
Now we are moving forward.
Okay.
What?
Now we are moving forward with
What is that? Yeah, one dimensional
what is
potential,
that?
right?
Yeah,
So
one dimensional
again, this is
potential,
very nice,
right?
interesting concept.
So
Okay.
again, this is
Till
very nice,
this point,
interesting
if you have
concept.
no
Okay.
doubts, can you
Till
please
this
react
point, if you
something?
have no doubts, can you please react something?
Yeah. Can you please react
Yeah.
something?
Can you please react something?
Can someone also?
Can someone
okay,
also?
I'll do it myself. One
Okay,
sec.
I'll do it myself. One sec.
Hello.
Hello.
Yeah. Okay.
Yeah. Okay.
Just give me a second, guys. Sorry for the
interruption.
Alright, so we'll move forward. So what do we have here?
So what do we have here?
An one-dimensional potential
An
belt.
one-dimensional
So,
potential belt.
This is
So,
an infinitely
This
deep,
is an
long,
infinitely
well,
deep,
okay?
long
So,
well. Okay. So
this
this
potential well. So you are
potential
trying to.
well.
So what is
you are
the
trying
objective?
to. So what
The
is
derivation
objective?
subjective is
The
to find
derivation subjective is to find the
wave function of that particular
wave
electron,
function of that particular
which is getting
electron,
trapped this
which is
infinitely
getting
deep
trapped this
potential.
infinitely deep potential.
Amazing guy. Okay. So you are trapping an electron.
You are trapping
inside
an
an
electron
one-dimensional
inside an
potential well. Only
one-dimensional
this particle can
potential
only
well.
move
Only this
between
particle
this
can
and
only move
Let's name
between
it
this and
x.
this. Let's name it
Can
x.
only range from 0
X
to L.
can only range from 0
This
to
is
L.
infinitely
Okay?
long.
This is
Wave
infinitely
function
long.
can only
The
exist
wave function can
between
only
what?
exist between
0
what?
to L, 0 and L not
0 to L,
included.
0 and L not
Okay.
included.
And the
Okay?
potential has
And
to be
the potential has to be
infinite
what?
outside of this.
Infinite outside
Because
of this.
again that's
Because
not
again
possible.
that's
And
not
the
possible.
potential has to be
And the
what?
potential has to be what? zero inside this, right? So consider particle trapped inside infinitely long potential well. The electron is restricted to moon this, and we know this thing. So we have to find the expression for the wave function of it. Let's try to recall our one-dimensional potential which we had minus h cross square by 2 into dou square psi by dou x square plus v psi is equal to e psi. This is what we had, right? But again, this does not give us the expression for psi, right? This was not useful for us. So let's try to put the same history out. So what happens? E minus v into psi was nothing but dou square psi by dou x square into minus 2m by h cross square. This is what we had. Remember? Now I want to deduce an expression for psi by comparing it with the sort of differential equation, because none of us know how to solve second order differential equation. So we have to compare it with the form only. So the form is nothing dou square psi by dou x square plus k square psi is equal to what? 0. If this form is going to be there, the psi can be written as what? A sin kx plus b cos kx. Just generalize it. Okay? If it is going to be of this form, just write psi as what? A sin kx plus b cos kx. Just remember that. Okay? Now how do I write this in this form? I can just take everything that side. Right? So dou square psi by dou x square plus 2m by h cross square into e minus v psi is equal to what? 0. And since v is equal to 0, it is just e. Right? So 2m by h cross square into e psi is equal to 0. Very nice. Now what am I going to do with this whole expression is going to be called as k square. We'll be using this towards the end of this. Remember this, right? 2m e by h cross is nothing but what? K square. Remember that. Okay. So what happens? So I compare this form nice. Okay, so k square minus sin what represented as a sin kx plus b cos kx. Now let's just substitute it. But again, I don't know what is a. I don't know what is k. I don't know what is b. What am I supposed to do? Right? There's a glitch here. So what happens? I have to deduce an expression for that. For that I use the conditions, right? What is the condition? Give me a second. The condition is your particle can only exist between x and between 0 and L and cannot exist at 0 and L. Okay. So at x is equal to 0, your psi is going to be 0. At x is equal to L also, your psi is going to be what? 0 only. These are two things which you can use. Let's just use it. At x is equal to 0, psi is 0. So psi is equal to 0. A sin 0 plus b cos 0. We know that cos 0 is 1 and sin 0 is 0. So 0 is equal to 0 plus b into 1. So b technically becomes 0. So this just tells me that this term does not even is needed. I can just neglect it. Right? So it becomes what? Psi is equal to a sin kx only. A sin kx only. Okay. Now I can use the condition for L now. X is equal to L, psi is equal to 0. So 0 a sin. Because I still have variables, no, I didn't find them. So I'll keep using this. So KL. Now this becomes a 0 is equal to sin KL. 0 by s 0. Now what happens here? When is the sign of function 0? When that function will be integral multiple of pi. When that KL can be expressed as n pi. Right? So KL is equal to n pi. Right? You can write k as what? N pi by L. N pi by L because I want k only. Right? So what happens? Because L will be given anyways. Right? So k is equal to n pi by L. So I can substitute my psi as what? See, eventually my psi is getting to the perfect form now. Right? So a sin kx was there. Since k is going to be n pi, so n pi by L, so I can just substitute n pi. X was already there by L. Right? A sin n pi by L is going to be what? Your psi. Your psi. Okay? So psi is equal to a sin n pi by L. Now again, still I don't know A. I don't know A. What am I going to do? I know one property now. Okay. What is that? Square integral. Right? Integral minus infinity plus infinity. Psi star should be what? 1. But there is no need for minus plus infinity. I just know that the particle is between 0 to L only. 0 to L only. So I just take 0 to L, psi star is equal to 1. Right? So what is psi star? All these are real functions only. So psi star is just psi only. So this is just psi square. Mod psi square. Okay. So what happens? That is just going to be what? 0 to L. 0 to L. 0 to L. Okay. This could come. This could come. Okay. So this is nothing but a square sin square n pi x by L and dx is equal to what? 1. So this is what we have. Again, a square constant I can take outside. Okay. Sin square I have to integrate it. I can put it as 1. Okay, I'll just integrate it first. So I'll just put that form and then integrate it first. So 1 minus cos 2x by 2. right? What is x here? X is nothing but n by x by l. N by x by l. N by x by n. Okay, so this is what we had, right? 1 minus cos 2x by 2 dx. I just expressed this in the form. Okay, now I have to integrate this. This has to be 1 by the way, right? So I have just integrate this now. So what is that going to be? A square, I can take 2 common, a square by 2. Now integral of 1 is going to be x minus cos 2x integral is going to be what? Sin 2x, sin 2 into n by x by l by 2 n pi by l, right? And then nothing else. So 0 to L. Okay. So this is going to be what? 1. Okay. So integration is substitute, right? So 1 minus cos 2x. So cos 2x is going to be nothing but sin 2x. I took 2 common anyways, right? So it is just a sine of 2 or something. Okay. So what happens here? Again, what are you trying to prove? You are again trying to prove. You are again trying to prove what you are trying to prove what is the wave function is going to be. What is the constant A is going to be. That was the whole objective here. Now, what are we supposed to do here? We took the derivative of cos, we got sine, we took the coefficient of x, which was nothing but 2 and pi by l, and now let's just integrate from 0 to l. So what happens here? Again, so again, what are you getting? A square by 2 into, you substitute L here, what happens? L minus. You substitute L here, what happens? This becomes 1, 2 and something. You substitute L here, L by L is going to be 1. So you don't sin 2 and pi something. Sin 2 and pi something will always be what? 0. Because sin n pi is always 0. So L minus 0 plus, minus, x substitute 0, 0 minus, sin of 0, 0. So it is just going to be what? 1. So A square, L by 2 is 1. So nothing but L is going to be root of 2 by L. Root of 2 by L. That's it. A square L is equal to 2. So L is equal to 2 by A square. So, A square is equal to 2 by L. A is equal to root of 2 by L. That's okay. So as simple as that, you substitute, you found the expression for A also. So you can just write, upgrade your wave function. A is nothing but root of 2 by L sin n pi x by L. N pi x by L. So this is your entire wave functions formula for one-dimensional potential, right? When you have more dimensions, you can add them here. So what are, let's say you have y also, root of 2 by L sin n pi x by L into root of 2 by L, Lx, Ly, sin n pi y by L, and then Lz, sin of n pi z by L, right? So you can always do that. So that is the expression for wave function. Again, energy is also important equally. Okay, understand that also. So what is energy going to be? We know that energy is going to be, 1 second. So we know that energy is going to be what? We don't know actually. So we know that K is equal to, because we derived something there. Remember, I told you we using the last key. We derived that K square is equal to 2 by h cross square. Remember? I don't know if it is h cross square or h. 1 second, I have to refer. H only, h cross. 2 by h cross. Right? So this is what we had. Now you know that K was nothing but from the derivation you obtained K as what? You obtained the K's value as n pi. 1 second, was n pi by L, I guess, right? Yeah, n pi by L, right? So what happens here? 1 second. Just streaming something. It is always glitching. 1 second. Okay, great. So we had what? K as what? N pi by L whole square. This was nothing but what? 2e by h cross is nothing but h by 2 pi. I'm just putting that here, right? So this is just n pi n square pi square by L square. Now we have to reduce the expression for e. That was the whole objective here, right? I think it was h cross square. Something is wrong here. 1 second. Oh, it was h cross square. I took wrong here. Okay, sure. Right? So what happens here? So this is squared. This is squared. This is 4. Okay. So what happens here? You have to reduce the expression for energy E. E will be nothing but n square. You take h square by 4 into 2 is 8. M you can take down M, and N square will be there L square. That's it. N square H square by 8 ml square. Pi square cancels out. Pi square cancels out. Okay. So N square by 8 ml square is your expression for energy. Okay. So again, when you have other states also, other quantum numbers also, you can write N as what? X square plus Ny square plus Nz square. When you have other length, what do you do? You have to separate everything and write. If you have other lengths also, when we are rectangle kind of thing, right? How do you write it? Write as Nx square by 8 ml square, 8 ml square plus Ny square square by 8 ml square and so on. Right? So that's what we do. So that is the energy expression. Okay. And you can have energies. So this formula gives us an intuitive thing. Okay. I can have same energy for different states. Remember, different combinations of quantum numbers. I have 1, 2, 1, 1. I have 2, 1, 1. I have 1, 1, 2. In all these configurations, you plug it in, it will always be 1 square plus 2 square plus 1, or 2 square plus 1 square plus 1, or 1 square plus 1 square plus 2 square. That will always be what? 6. That will always be what? 6. Remember? So if that is the case, my energy will always be same for all these configurations. Then you call these states as what? Degenerate states. You call this principle as what? Degeneracy. Okay, degenerate states. So whenever you are asked about degeneration, you just write all these configurations. You will prove that energy is going to be equal for all these configurations. You will also prove that what is the value of that energy. That's it. Okay. So that is about one-dimensional potential. Well, yeah, I think you should know how to plot these graphs better, right? When your n is going to be 1, the plot this is A, just run A, okay? Psi 1, psi 2 is done it for all the n, right? So n is equal to 1 here, 2 here, and 3 here. When n is equal to 1, what is your energy? H square by 8 ml square. This is 4 H square by 8 ml square, 9 H square by 8 ml square. When you take the modulus, everything will just come on the upper side. This represents probability. Right? So that's also there. Now you can just do all these stuff. You multiply stuff with 3 dimensions, add stuff with 3 dimensions, and you can do all that, right? And degeneration also. Yes, instead of the particle with same energy but distinct wave functions. There are different wave functions because they have different nx and y and z. Still, they are having same energy, degenerate states. Okay. So that is the thing. The state of a free particle is described by the following wave function. Find A using a normalization condition. What is the probability of finding the particle within this interval? What do you do? Firstly, the wave function is represented by A. See here, the wave function is actually A here. Okay. Then they are telling me find the probability of finding the particle within this interval. What do you generally do? Probably meaning 0 to 2b mod psi square. Right? That's what you do. But I'm not able to say this because I don't know what is A. I don't know what is A because I know A, but what is A actually? That we don't know, right? So to derive that, I can just use my square integral property. What is that? Minus b to 3b, the particle has to exist. So A square dx would be nothing but what? 1. Right? So A square into this can just be 1 dx. So x. So 3b plus b is equal to 1. So you will eventually get A, you will substitute here, you will integrate, you will find the answer. That's it. So that's the intuitive approach here. Just whenever you are asked to find the probability in a certain interval, you will first find the wave function. Okay, from the given condition. In this case, wave function is given as A, but I don't know what is A. I can just integrate square integral. So I can put the limits, I can integrate it, put psi square is equal to 1. I can get the value of that and I can substitute I can find the wave function now without any arbitrary constants. I can put that in the wave function probability for finding that in the respective interval. Find the energy separation of the first two allowed energy levels of an electron confined in a cubical box of this side and so on. Okay. So find the energy separation of the first two allowed energy levels. Okay. This could be what? Configurations like 1, 2, 1, 2, 1, 1, and 1, 1, 2. Basically, 1, 1 could be a ground thing. Okay, ground state. And when you have something excited, it will be what? The state 2, right? So all these states are there. All these have the same energy. That is going to be what? The same energy for everything. Degeneration is going to be observed. Find the energy separation of these things. What do you do? You know energy formula, right? Energy formula is n square by 8 m square. 8 m square. It is n square is n square plus n square plus n square. Okay. So you will substitute L as what? 1 nanometer in one case, 1 millimeter in one case again. You will try to find the ground state and first two allowed states. So you can take any of these in the second state. This is the second state. Okay. The first state you can take 1, 1, 1. You will find the energy for this. You will find the energy for either of them. you will try to subtract the energies for both. Okay, this is the first one. Okay, you will substitute L is equal to something for finding the energy in the first case. Okay, first apart, and you will find the energy separation. Simply 1 millimeter also you will find the energy separation. You can easily find it. Okay, so that's also there. Now, an electron in a cubical box of size, particular nanometer is subject to influence of electric field such as the length of the box increases by this, whereas breadth and thickness remains the same. Find the energy difference between the states with this quantum numbers before and after the application of electric field. Again, not so tough. Firstly, you will consider before considering electric field. If that is the case, length is equal to breadth is equal to height. Okay, in that case, you can easily find the energy expression n square h square by 8 ml square. But again, 1 come on, you will find separately. 3 come on, you will find separately, right? And length, breadth, height are all equal. Fine. Now, in the second case, when the electric field is going to be applied, length increases by 0.05 nanometer, but breadth and thickness remains the same, right? So you will try to take n square h square by 8m, Lx square alone will be different. Ny h square by 8m, Ly and Lz will be the same, which is going to be breadth and thickness. Okay, and yeah, so that is a key idea here. So and you can apply Nx, Ny, Nz for both these cases. Okay, and you can check how energy is going to be different. And energy level is an energy level diagram. Low level energy, what is that? High level energy, what is that? What's the difference between the energy levels? You can just you just have to show it. Just put some lines. See, this is the energy level of this. This is the energy level of this. This is the difference between these two energy levels. These are the states available in these energy levels. Okay, so you can just show that. Okay, not going too deep here. The state of a particle is described by the wave function. This find the probability of locating the same thing. You see, A bar minus kx is given. I don't know what is A. First, I'll put minus infinity plus infinity. A bar minus kx. Find the value of A, right? And then when I found the value of A, I can just substitute A here. I can just what are they asking? They are asking the probability of locating this particle from 2 by k to 3 by k. I can just put it. I can substitute the value of K here. I can find the probability here. I can find the probability here. Okay. So yeah, that is the whole point here. So till this point, any doubts? We are going to complete quantum. If there are no doubts, please react. Okay. Now, classical free electron theory. What happens? Valence electrons are free to move about in a volume of metal, which is composed of iron cores with nucleus. The electrons move in a uniform potential field. Okay. The electrons move around randomly and suffer scattering due to collisions with stationary ions. Okay. These guys, see, I understand it's a free electron. This guy has the complete independence. He can go anywhere he wants. Okay. He moves in a uniform potential field. Okay. But again, he can go and collide stuff. He can lead to instantaneous abrupt change in the velocity. Very nice. Okay. But yeah, this guy can just go around, right? The mean, okay, this are all just formula based things. The mean free time between two successive collisions and therefore the mean free path lambda is independent of the velocity. Okay. And that is given by apart from ion electron collisions, all other interactions are ignored. 3 electron approximation, there is no electron phonon interaction. We are not getting deep into this. If you have doubts, let me know. Independent electron approximation, there is no electron-electron interaction or electron interaction with positive charges. There are going to be electron collisions though. There are going to be electron collisions. Electrons with the ions which are present in the metal, those collisions will always be there, right? So, yeah. So they're just calculating the average. They're just showing the average velocity of an electron. You know, K is 1 10 to the power minus 23, and T is like number 300 Kelvin in this case, and M is for an electron is this. So this is the average thermal velocity of an electron. Understand this? 1.17 10 power 5 meter per second. Remember? Yeah. Okay, but that is not very much required. So understand this. Whenever they ask you about electron field theory, just write this. Okay. So what is that? That was classical, by the way. And now quantum electron theory says electron levels are discrete. They are not continuous. They obey Pauli's exclusion principle. They obey Fermi Dirac statistics. Only two electrons can occupy one energy level. Okay. Only 2 electrons can occupy one energy level at two opposite spin, right? And all the electrons which are present in whatever atom we are talking about, they all have very distinct. They cannot have the same set of 4 quantum numbers. You take 2 electrons in any set of atoms, okay? None of them will have the same set of 4 quantum numbers in an atom, right? So that's the thing. Also there, right? Therefore, all the electrons in a metal do not take part in the reaction part. Only a subset of them, we call them valence electrons. The free electrons move in a uniform potential. We know that will be there. Free and independent electron approximations are going to be there. Okay. Okay. Yeah. So, the same thing repeated. And here electron interaction exists. Okay. Yeah. Just remember that. That should do too much things. Yeah. Okay. One second. Okay. I think that should do. That's just theory. Okay. Now talking about Fermi function. A Fermi function is a function that tells you the probability of finding an electron with an energy level E. That's it. Okay. The probability of finding an electron with the energy level E is going to be the f of E function, which is the Fermi function. That is given by the formula 1 by 1 plus E power E minus E by kT, I guess. Once again, long back I learned. 1 by 1 plus E power E minus E by kT. So this is what we have. Now EF is going to be the Fermi level, Fermi energy level. Okay. K is Boltzmann constant, T is time. Yeah. So T is temperature. Sorry. Yeah. So this is going to be F of E. Right. Now, Fermi function gives you a lot of things. I'll tell you. Okay. It represents the probability that a particular quantum state of energy E is occupied by this electron. Right. Now there are cases. Let's just take cases and see. If E is going to be greater than EF and T is going to be 0. So firstly, okay, what happens when T is 0? What happens when T is 0? When T is 0, this whole thing becomes infinity, no? 1 by 0 something kind of thing. So it becomes infinity. But whether it will be positive or negative infinity depends on whether E is greater than infinity, EF or E is less than EF. Because based on whether it's positive infinity or negative infinity only, E power thing can be defined. We know it, right? Because we know E power infinity is infinity, E power minus infinity is 0. Right? Limit extension infinity, E power minus infinity. Just do that. Okay. So we know that thing, right? So we can just substitute that. So based on that condition only we are taking. That's why we took T is equal to 0. Let's take E is greater than EF. If that is the case, then this is going to be a positive infinity. 1 plus E power positive is just 1 by infinity is 0. Right? What is the probability that you have an electron above the Fermi level at 0 Kelvin? What is the probability? Literally 0. This gives you a concept itself, right? You take so how are the things bands separated? So this is going to be your valence band. This is going to be a conduction band. Different energy levels overlap when you have metals and all, right? You remember? So valence band, conduction band, and Fermi level will lie somewhere here based on whatever temperature is going to be and so on. We'll be using the formula in general case also. So EF is going to be somewhere here, right? Now when you see at 0 Kelvin, okay, you're trying to see the energy, so the electron, the probability of finding an electron above EF level, the probability is literally what? 0. Is literally what? 0. Because it will not have excited itself. You didn't even supply temperature, you didn't even supply anything. How is that supposed to be? Right? So yeah, that's there. Now what if E is going to be less than EF? If that is the case, 1 by 1, what will happen? 1 by 1 plus E power minus infinity will be just 0. That'll just 1. That'll just 1. So when you're talking about E less than EF, the probability of finding an electron will always be what? 1. It will always be there. There is no doubt in that. Right? So that is 1. Okay. What happens when both are 0? What happens when both are 0? Sorry, when both are equal? When E is equal to EF and T is equal to 0, then what happens? It is indeterminate form. Okay, indeterminate form. Now, I want to have a definite form. Let's just contain T is not equal to 0. Okay, T is some greater than 0. Okay, obviously it's not less than 0. And E is going to be equal to what? EF. If E is going to be equal to EF, E minus becomes 0. So E power 0 by KT, but this time T is not 0. There T was 0, that's why indeterminate. So T is some number only, so 0 by some point number will be 0. So 1 by 1 plus 1 will be there, E by 0 1. So 1 by 2 will be there. So for non-zero temperatures, Fermi level represents the energy level at which probability of occupation by an electron represents what? 50%. So Fermi level represents some very basic, right? So 50% probability, right? So that is also there. So therefore a Fermi level can be defined as the highest energy level occupied by an electron, and it also at 0 Kelvin. That's what we saw, right? More than that, probably 0. Less than that, probably 1. So highest energy level. And also represents for the temperatures above 0 Kelvin, the energy level at which the probability of occupation of an electron is 0.5. Okay. Now the number density of electrons in a solid in an interval of energy D above E is therefore equal to density of allowed states with energy in the interval D about E into probability that is occupied by an electron. Okay, understand this. You want to find the number density of electrons in a particular solid. About 10 D. Okay, fine. See, for finding the number density of electron, first we find what are the density of whatever states which are available. Which are number of states which are available. We'll be using the derivation for number of density of states anyways. Okay. But remember, we will first do the density of states multiplied by what is the probability that it is actually an electron. Right? So the density of all states in that energy level multiplied by the probability that it is going to be an electron gives you the number density of the electron itself. Right? So that is the whole idea here. So whenever you are asked to find the number density between an interval also, you just put interval E1 to E2, that energy interval, into G of E, F of E, dE. That's it. F of E is the function which gives you the probability. G of E is the density of states. Okay? Now, use the following function to obtain the value of F of E for E minus E F and D. So, direct formula, E minus E F is given, K is not given, but T is given. You know what is K, 1.8 delta minus 3, this is substitute the answer. Use the following function to evaluate the temperature with 1% probability that an electron in a solid will have energy 0.5 electron volt above EF of 5 electron volt. Okay. So this is interesting. What are they telling me? The probability is actually 1% for locating an electron. Okay. So following function is the probability which is nothing but 1% which is 0.01. Super, very nice. What are they telling me next? In a solid with an energy 0.5 electron volt above EF. Right? 0.5 electron volt above EF of 5 electron. What? 5 electron volt. One sec. Is 5 given anywhere here? Okay, anyways, okay, difference. EF was somewhere around 5 electron volt. The difference was 0.5 and we are looking for 5.5 here. So what is the probability? The probability they are telling me, probability that it is occupying the state is going to be what? 0.5, sorry, 0.01, 1% basically. What is the temperature? That's it. Direct formula substitution. What is that? Just substitute F of E as 0.01 by 1 plus 1 plus E, 1 by 1 plus E power. E minus EF by KT. I know what is K. I don't know what is T. I know what is E minus EF because I know the difference between the energy levels is 0.5. I know the difference between energy levels is 0.5 into electron volt. I want to put this into SI units because everything I'm using SI units. So I just substitute this as what? 1.6 into, so you know this, right? 1 electron volt is what? 1.6 into 10 power minus 19 joules. Okay, so you just use that. So this becomes SI units. You can substitute everything you want. So E minus EF is also known. You can substitute in the value of just take logs and stuff. Okay. So that becomes Fermi-Dirac statistics. Just know the Fermi-Dirac theory and know that you can find the probability of electron with this particular energy level E. Okay. And you can also deduce an expression for the number of electrons around the particular state, which is very basic for semiconductor testers. Okay. Now moving to the last part. Give me a second. And till this point, anyone has any doubt? If not, can you please react? Right. So let's move forward with density of states, right? And the average energy of electron at 0 Kelvin, in which we use what? Density of states application. Okay. So we just derive this formula. We are just going to use this formula in deriving what? Expression for density of states. Energy of any allowed level n for a free electron confined in a cubical box is given by the formula what? N square H square by 8m square, remember? Right? And we also know K is equal to N pi by L, in which we use there. The same formula we are using here, right? So the number of levels between E and E plus GV is nothing but the number of allowed levels between K and K plus GK, right? Which is N plus N and N plus Dn. Something related to what? One second. Not one second. Yeah, and N plus Dn, right? So basically, these are all related concepts in which energy depends on your k values and k value depends on n value, right? So you know that n square is equal to n square plus n square plus n square, right? You know that n e is equal to what? E is equal to n square by 8m square. So technically what is n square? N square is, you can take that this side, because E is n square by 8m square. N square will be 8m square into n by n square. 8m square into n by n square, right? So let's just put that in note, okay? Let us represent each n value in 3 space, so that's different by n, x, y, and z. Okay. I remember multiplying n by a constant as h cross x by L gives momentum B, and this space is called momentum space. Okay, fine. In this space, all the points that have the same n value lie on the same surface of the spherical shell. They'll all have the same energy. But same n value indicates the same energy. The spherical shell of radius n of radius proportional to n in the momentum space represents the equipotential surface. So all this here is given to understand that whatever n values you are talking about, whatever points that have the same n value, right? Whatever points that you have, right? If you multiply that, whatever n x, n y, and z, you multiply that by the constant n, they'll all have a certain momentum. They'll all have a certain momentum. And you know, the same n value means same energy. So it's all the same equipotential surface which you're talking about. This is a sphere kind of thing, right? That has the same energy, right? So we all know that. So just take a note of this table. Okay, just understanding, self-explanatory, I guess. You take unit volume. Okay, what do you want to find? Number of levels between n and n plus n. Volume enclosed between this. Unit volume of the positive quadrant of the momentum space contains one allowed energy level, which is 1 of k naught. And when the size is going to be 2, the volume is going to be 8. Okay, yeah, they're talking about this. We also talked about degeneracy, right? So again, these are all degeneracies. E naught comes when you have 1, 1, 1. E1 comes when you have all these configurations. E2 comes all these configurations, right? All these are all shared by what? Equipotential surfaces. When you have different configurations, then based on that, they're all will be in the same energy sphere, right? So they're just showing that momentum space like that. Now you have to find the number of states in a particular E and E plus G, what is the number of states? That's your whole objective here. So E plus G can be represented by a sphere of radius n plus Dn in this space. So you have a radius of n and you have a very small change Gn. So you have n plus Gn, right? The number of levels between E and E plus G will be given by what? The number of levels between n and n plus Gn easily. And the and that can be easily taken as volume. The volume enclosed between the spheres of radius n and n plus Gn. That's it. Right? So what is the volume? You know that sphere's volume is nothing but what? 4 by 3 pi r cube. 4 by 3 pi r cube, right? So we can just take what? 4 by 3 pi into r cube. What is the outer one? It is n plus Gn whole cube. This is spherical shell. You remember? This n plus Gn is the whole thing. N cube is this interior thing. That gap, right? N plus Gn whole cube minus n cube. So you got this expression, and you can just simplify it. You can take the dn's out. Dn's will be 0. You can take cancel it out. Something will come. This is the whole cube formula. You will get what simply 4 pi. Okay, let's just do. Yeah. What do you have? One second. N cube plus dn cube plus 3 n square dn plus 3 dn square n minus n cube. Okay, so this is what we have. Again, we can take what? We can take n cube and minus n cube goes off, and then we have dn cube plus 3 n square dn plus 3 dn square n. Now you can take what common? You can take you can ignore dn's. Dn's will be just 0. Okay. Now dn square will again be 0, just 0. So this becomes 0. This becomes 0. Actually, this becomes 0, but n square. Okay. Good amount of quality. Let's not take neglect plus now. So what happens here? 4 by 3 pi we had, and now it's getting multiplied by 3 n square dn. 3 gets cancelled, so 4 pi n square dn. That's what we have. Okay. Ignoring higher powers of dn. That's it. Nothing else. Okay. So yeah, again, you are only interested in finding. And there are no negative values for n, x, and y, z, right? So, but the sphere gives you all the 8 octants. Just like when you have 2D, you have quadrants. In 3D, it's octant, right? So, you are only considering 1/8 of that particular sphere, right? 1/8 of that sphere. So, we got 4 pi n square. So, just divided by 8. So, you have pi n square divided by 2. So, that's what you have, right? Now, we are just substituting the n square in the formula we derived here. Okay. So what do you have? The number of levels between E and E plus G is pi n square dn by 2. You have to express n in terms of known quantities. You just express the E, remember? So n was nothing but what? N square we put it as 8 ml square E by S square, remember? So you can just take the root of it, right? So n is equal to root of 8 ml square by S square E, and n square is just this one, right? Now we have to find what? We have to find the number of levels between E and E plus G. And how are we finding it? So firstly, let's try to differentiate this equation. So we get what? 2 1 and 2 1 dn, right? So 2 1 dn will be nothing but what? Differentiate this. 8 pi ml square by S square will be constant, will be d, right? So we got ndn. Ndn will be nothing but what? 4 ml square S square d. Now we have to find the expression for what? We have to find the expression for 1 second. Right. So what happens here? Again, in order to find the number of levels between E and E plus G, you have to find n square dn. That was the formula. Pi by 2 into n square dn. But I don't know how to find n square dn. That's why what I did was very simply I know what is n. I know what is n dn. So I can just do n and then here I can multiply it here. That's what they have done. So n square dn is just n into n dn. I know what is n. I can just substitute the entire n here. That's just root of something. And n square I know I substitute there. So I will get the similar expressions 1 power 1 and power 1 by 2. So power 3 by 2 into root e will come. E is outside because that's not shared by this expression. Now you can just substitute this n square dn in the formula pi by 2 into n square dn, right? And this just gives you pi by 2 to 1 by 2. Again, I can just take few things out which will help me in taking the powers easy. So 8 m square by 8 square will be there. 8 is nothing but 2 cube. Okay, 2 cube. Right? What are they doing? Okay. 8 they are writing as 4 into 2, so that this is power 1 by 2, right? So 4 into 2, 1 4 can be taken as just 1 2, right? 1 2 will come out, right? So 2 square, 1 2 will come out, okay? 2 ml square, again L square, remember? L square 2 to cancel out, L cube will come out, okay? And H cube will also come out, right? So you will just have this expression. Right? So 2 will always be there, 2 power 3 by 2. And here you had what? You took 1 2 outside, you took 1 L outside, you took 1 H outside, already 1 by 2 and pi by 2 was outside, right? So pi by 4, 2 cube by 2, 3 by 2, L cube into DD. Just write this is a nice form, that's it. Pi, so what is the nice form? The nice form is this. 4 pi. 1 second. Yeah, so this becomes sorry, yeah, right. So this gives you a formula which is 2 pi by h cube, 2 because 8 and 4, so 2 pi by h cube, 2 over 3 by 2 root ED. Again, understand this is only talking about number of levels between E and E plus G. But again, in unit volume of materials, again in your definition of specific unit volume of materials is also there. You have to divide it by L cube. Right? L cube will not the formula. So 2 pi by h cube, 2 over 3 by 2 root ED is the number density of states between E and E plus G, taking into account 2 possible spin states. Then again 2 possible spin states, not positive and negative. You have to multiply the whole thing into 2, right? So we only derive it for all the things, but there are going to be spin states can be plus and minus. So you can multiply it by 2. So that will give you the final formula, which is very, very important. 4 pi by h cube, 4 pi by h cube into 2 power 3 by 2. Into root ED. Just remember this 4 pi by h cube, 2 over 3 by 2 into root ED. That will give the number of states per unit volume in the energy occupied by that can be occupied by charge carriers between the interval E and E plus G. Okay. However, the number of charge carriers per unit volume will depend on the yeah. So this is the density of states. This is the density of states. But how do you define the number of charge carriers? We just define the density of states. The probability that the charge acquires sufficient energy to occupy these states. Right, so that is given by the forming function. That's given by the forming function. So the density of states forming function that level gives you the number of electrons and so on. Right. So just remember that. Okay. You can have graphical representation of your probability. You remember here when it was less than EF, the probability was 1. Okay. When it is going to be what? Greater than EF, the probability was 0. In the case of time is equal temperature is equal to 0 Kelvin. When temperature is going to be greater than 0 Kelvin, we had a half here. Remember that's the case. Right? So that's how the graph like. Okay. At exactly when you have E is equal to EF, it will be 1 by 2. The probability will be 1 by 2. Just remember that. Okay. So that's also there. So just remember that. number density is formula. I just remember all these graphs. Yeah, nothing else, right? So find the electron density, okay, of for metals at 0 Kelvin. What do? Density of states, Fermi function. What is the density of states? This is the density of states. I took the constant outside. Do TD already there. Okay, and one second. What are they asking me? For metals, so they're asking me for find the electron density for metals at 0 Kelvin. We know that for metals at 0 Kelvin, all the levels up to energy level EF is occupied. All the levels at EF is going to be occupied. So what is the probability of finding them? One. Okay. So f of e automatically becomes 1. You just have to integrate this function and get this value. That's it. Okay. Nothing else. Nothing so much complicated. Don't worry. Okay. Finally, find the average energy of Kelvin. Average energy of electrons in metals. What is the average energy of electrons?
Find the total energy divided by volume. Find the total energy divided by volume, right? So, so the number of electrons divided by total number of electrons divided by volume multiplied with the energy of each state. Basically, energy of all the electrons will be nothing but the number of electrons multiplied with the energy of each state divided by the volume, right? So that's what we do. So firstly, let's compute G of E F of E, right? So G of E F of E multiplied by E because energy of each state multiplied by the number of electrons in each state will give you what? The total energy divided by volume. That's it, right? So let's just obtain this 4 pi by h cube d1 power 3 by 2 root e dE, and there's one more e. You can just find the value of this, and you just have to divide by what? So we obtain this expression for the total energy of all the electrons per volume, right? Up to EF. Now total number of electrons you just divide it. You will get the average one. Right? Total energy divided by total number of electrons will be the average energy of electron. No, so that is what it is. Okay. So yeah, so we started off with finding what the density of states here, and we found various formulas for finding the average energy from energy functions. We also find the expression for the a lot of things in this chapter, right? I think these things are there. Okay, we have done all of this. We have derived the density of states. We have just given the density of states alternated the definition, which is the same almost. Okay, fine. So let's just revise quantum physics. What happens here? Firstly, we learn about different quantum theories, how classical theory failed and stuff, and then we learn about Paul's postulates. We learn about what is that? De-Broglie's principle. We learn about wave function basics, and then we learn about how to derive the wave function, how to derive one-dimensional time different equation, one-dimensional three-dimension, and then one-dimensional potential and 3D box, and then we go to density of states, and then we go to number density and stuff, and that's when we end it. Okay, so that's the end of quantum physics. If you have any doubts, please do tell me. We'll be using the formula for density of states in the next chapter, which is semiconductors. Okay. So any doubts here? Anyone has any doubts? I'm so sorry that I cannot give my full potential today, but yeah. Any doubts still here? Yeah. Feel free to please react whenever you have something. Okay. Wait. One second. Can someone please check the YouTube live and let me know if my voice is echoing or something? Okay. Can you please do that?
We might be shifting acoustics and ultrasonics tomorrow. Is that fine for you all? Acoustics, ultrasonics, and fiber optics tomorrow. We'll complete semi today. I think that should be the goal for the day. Is that fine? Or do you want me to complete? I won't have any issues. Why is it going? 1 second. Hello. Hello. Yeah, I observed that voice was echoing. I'll see. I'll sort it out and come. Also, I'll have my dinner and come. Yeah. We'll meet at 9:15, 9:10. We'll meet at 9:10 exactly. Okay. And yeah, 9:10. We'll complete some intrinsic. So we'll complete only the intrinsic part of semiconductors. Fazil is not available as of now. We'll see if we can plan a session tomorrow, and we'll just complete acoustics and ultrasonics today. Yeah, acoustics, ultrasonics today, as well as intrinsic semiconductors today. We are only leaving extrinsic semiconductors tomorrow. Is that fine? Can you please react if that is fine? Thank you so much. Okay. We'll meet at 9:10.